Okay, so thank you, Klaus, for the introduction, and special thanks to Dr. Alex Choi, from Deutsche Telekom, the Senior Vice President there and the Head of Strategy and Technology and Innovation and CEO of Oran Alliance, for the very important outside view that you actually gave us on the important and the relevance of ZSM, the opportunities. And by this, I would like to hand over to Uwe Rosenbach from Nokia, the rapporteur of ZSM 002 on ZSM Architecture, and he will give us some insight into the ZSM Architecture and its impact in the industry. Uwe, please.
Yeah, thanks, Nurit, for the introduction. So I hope my screen is visible now. I will first introduce to you the ZSM architecture as a framework for next generation automation platforms. I want to start my presentation with a citation from Anil Rao of Analysis Mason about ZSM. He basically said that collaboration among SDOs is critical to accelerate telco automation. ZSM is the glue that holds all of them together from an end-to-end automation perspective. And what I would like to do with you in the next 20 minutes is to look at this glue, to look at the ZSM architecture framework and how we have built it. In a follow-on presentation, I will then look at how we can exploit this architecture from an end-to-end perspective. So based on that requirement, it became pretty much obvious early in the work that we did at ZSM that we don't need to specify yet another system, but we need a flexible management framework. And we came up with a number of architectural principles that need to be obeyed by the design. So the first and fundamental principle is that ZSM architecture needs to be service-based. So the whole framework is built on management services, which can be composed, which can be exposed to service consumers, and which can be integrated with each other. For the interfaces, it is clear that they must be open, and as much as possible, they also need to be model-driven and intent-based. And we will have a talk later on that looks a little bit deeper also on that, I assume. Another important principle is the separation of management concerns. Management is pretty complex these days, and we introduced a means to modularize the whole design, which we call management domains, that allow the encapsulation of management complexity. Data are the lifeblood of automation, and therefore the ZSM framework must support sharing of data that are stored, or sometimes also called data at rest, as well as sharing of data that are streamed, sometimes also called data in motion. And last but not least, this architecture needs to be open and flexible enough that we can build on top of it closed loops at various levels, so we can drive the automation with or in this architecture framework. This is the result of the work. This is the ZSM framework reference architecture. And as I indicated, the basic principle was that it is service-based. And we see management services all across the board here. So these figures that look like lollipops, these are the services, the management services that are exposed. And they can also be consumed. So this is symbolized by the claw here, and they can be composed to achieve complex management tasks. A management service is a set of management capabilities that is offered by consumption, and it is offered by a management function. Management function can produce services. It can also consume services, of course, but it's a logical entity. So we didn't define management functions in ZSM. We only defined management services, and we leave the structure of the functions to the deployments. There's one exception from that rule, and that's the integration fabric. The integration fabric is a complex management function or set of management functions that can play the roles of both service consumer and service producer to fulfill its role to expose services. To expose services in an access-controlled manner to authorized consumers. Thereby, it enables the interoperation and communication between the management functions within management domains. We call this the domain integration fabric, or across management domains. We call this the cross-domain integration fabric. Further, for the sharing of data, we have cross-domain data services. And I was mentioning the separation of management concerns. We have management domains here. Each management domain is a scope of management that can be delineated by a number of different kinds of boundaries. And we have a specific end-to-end service management domain that is capable of managing end-to-end services, as opposed to the management domains that manage network resources or infrastructure resources. I would like to zoom in now on some of the features of the architecture in detail. The first one is the separation of concerns in management. So a management domain, as we see here, is a scope of management delineated by different kinds of, or can be delineated, deployment specific, by different kinds of boundaries: technological, organizational, administrative, even geographical. So you can structure your set of management functions and management services by defining the different management domains. Technology boundaries play a different, special role, and we will look at this in more detail in the next presentation. A management domain manages infrastructure resources. It also manages services based on these resources. And it provides management services that can be consumed by other management domains. And thereby it decouples the inner domain details from the outside world. Each management domain can consume management services from other management domains, thereby allowing to build also a hierarchy of management domains. The end-to-end service management domain is a specific management domain that is specialized in managing end-to-end services. In ZSM, end-to-end services are simply services that span multiple management domains, so that are composed of resources or services from or managed by multiple management domains. Like a management domain, it can provide and consume management services, but it also has the role to coordinate between the underlying management domains with respect to the end-to-end services that this end-to-end service management domain manages. So, for instance, it can share domain services between end-to-end service instances. This shows the management services that we have defined. So I indicated at the beginning, we're not defining management functions, so we're not defining functional blocks, but we're defining services. And we have grouped the services. So we have basically a logical structure that can join together management services with related functionality. However, this grouping is purely informational. What is normatively defined are the services themselves. The grouping comes handy when, for instance, doing closed loops, because this is a little bit, the grouping is a little bit related to the main steps of a closed loop. We have services that collect data from management domains. We have services that derive insights and recommendations from these services that are analytics services. We have support for artificial intelligence and machine learning. We have services, management services that orchestrate domain services, and we have management services that control the domain resources. A similar structure has also been defined for the end-to-end service management domain, as we can see here in the middle. And we have two specific sets of services. We have integration services and we have data services. And we will look at those in detail in a minute. Let's start with the integration services. These services are produced by the integration fabric, and they fall in 4 categories. We have management service communication. This supports asynchronous or synchronous communication when consuming or producing management services. Examples are event notifications, streaming data, or the classic request response communication pattern. We have support for the registration of management services and their discovery. So service producers register the services they produce, and service consumers can discover the services they intend to consume. We have management service invocation support. This allows, for instance, to build service meshes by using the framework to route the service requests and responses instead of having to do direct invocation of the service from the service endpoint, which is also possible. And last but not least, the integration fabric is responsible for managing access to the management services so that only authorized consumers can access them. This functionality is delivered by management service exposure and access control. Let's have a look at data. I have already indicated data are the lifeblood of automation. And if you look at data in motion, let's go back to the integration fabric. So this is part of management service communication. This is notifications, this is streaming, but we also need to look at persisting data. There are quite a few categories of data that need to be persisted. Also, if you look at the need to support machine learning, you have to learn from historic data. And we see, or we have a performance monitoring data, we have fault or alarm data, we have trace, we have configuration data, log data, and data related to topology and inventory. And all these are persisted somehow, and typically they are persisted these days directly by the management functions that expose the related services. And we want to migrate to a storage in cross-domain data services. These services allow the storage of management data using some harmonized mechanism, and sharing these stored data with authorized consumers across domains. They also support the big data analytics that would allow uploading a set of analytics instructions to the producer of the data services. And then instead of having to download big volumes of data, you would only download the analysis result. This is just an optional extension of the data services, but it might be quite interesting when for supporting automation. Okay, so all these architecture features have been defined to support automation based on closed loops. We will have a detailed presentation about this, so I will only give a very brief overview. Closed loops need data, need knowledge about the state of the network, and they typically run in a number of steps. This here is an example called OODA, Observe, Orient, Decide, and Act. What you typically do is you monitor your network, you observe performance and faults, then you analyze what you have monitored and you derive insights and recommendations. Then you have to make a decision and you have to act upon it, influencing the network resources. And once this loop is finished, the monitoring will hopefully show a change in network behavior for the better. Yeah, I will leave more detail to my colleagues in their presentation, but I would like to give you an example how things fall into place. So here we see the managed resources. These are outside the scope of ZSM. We have service producers and service consumers. These are management functions. We don't specify them, but in a deployment we have them. Oops, sorry. There is a southbound interface of the management domain, which is defined by other SDOs, defining how resources can be managed. And via this interface, in our example, a management function that produces fault events receives information that there is a failure in the underlying resource layer. It shares this information via the integration fabric with interested consumers. In this example, we have two. We have an analytics component that is also able to learn. It consumes the fault notification. We also have the data services producer consuming the notification to store a time series of historic faults. The analyzer will determine the root cause and will share the insight via the integration fabric with a component that is a management function that is able to make decisions. And this management function will make the decision to reroute traffic via another route. And in order to act upon this decision, it will consume, again, another management service that is produced by a configuration manager. And while this management service is consumed, so this is basically, this was more push-based consumption. So communication pattern was push. This is service consumption based on the pull or request response communication pattern. So this request is basically sent from here to there. The service consumption is going the other way around. And the management function here will change the configuration on the router, and hopefully the fault events service producer will observe the alarm that it has seen previously to be cleared. So this is a very simple example how such closed loops could work in the ETSI ZSM reference architecture. I would also like to illustrate a little bit the role that ZSM foresees for the architecture framework in the industry. We believe that work done in other organizations, more specialized in particular technology domains, fits well into the architecture framework of ZSM, and it can help enabling the orchestration and automation of end-to-end service. And also, the ETSI ZSM specifications provide guidance on the design of management services to achieve automated end-to-end management solutions and architecture. To conclude my presentation, I have presented to you the ZSM Framework Reference Architecture, which is flexible and service-based. It separates the concerns of network domain management and end-to-end service management, and it offers an integration fabric and cross-domain data services that provide flexibility. It provides flexibility to integrate and compose management services, to provide management data, and it gives the foundation to build closed automation loops across domains. The ZSM framework architecture provides the glue to integrate work done in organizations such as 3GPP SA5, ETSI-NFV, ONAP, ORAN, and so on. Its concepts and principles are also used in service-based architectures developed in other SDOs, such as 3GPP, SA5, and ORAN. This brings me to the end of my presentation, and I would like to say thank you for your interest, and I'm handing back to Nurit.
Thank you, Uwe, for the insightful presentation on the ZSM architecture. And this architecture enables end-to-end solutions, in particular service or network slicing, orchestration and automation. And we would like to start with the first end-to-end solution that ZSM has worked on or is working on, which is the cross-domain end-to-end service lifecycle management. And I would like to invite again you, Rosenbach, the rapporteur of ZSM 008. So please.
Okay, thank you. So this is my second presentation today, and it illustrates how ZSM foresees the use of the architecture for a particular aspect for the end-to-end service lifecycle management across domains. So as I introduced in my previous talk, the ZSM framework separates the concerns of end-to-end service management and domain management. And ZSM 008, that's the number of the standard that we're developing, looks at how end-to-end service management and domain management interwork during the life cycle of end-to-end services. So we look at the interface between end-to-end service management domain and the management domains for the support of cross-domain end-to-end service lifecycle management. We basically do three things. We first define end-to-end service lifecycle management processes, typical processes. Of course, as I said, the framework is open, more processes can be defined, but we look at typical lifecycle management processes and how they consume the ZSM services. We also analyze, so this is basically top-down, then bottom-up, we analyze the northbound interfaces of different technology domains, and we document a mapping of the ZSM services that we use in the lifecycle management processes to the technology domain northbound interfaces, and we also document gaps. So the step one is basically to define the end-to-end lifecycle management processes. And what we did in ZSM 008 was covering three parts of the end-to-end service lifecycle. So not all parts, as you will see, three parts related to running the services. We start with onboarding processes that import the service models from the service design stage into the ZSM framework. And also, of course, for each such service model to set up the ZSM framework so it is able to create instances of these services. Service design is a step that is currently outside the scope of ZSM. So we import the result of that step. Then we looked at fulfillment processes. So processes that support the actual management of the life cycle. So they directly impact the life cycle of the end-to-end service instances using operations such as service instantiation, service activation, deactivation, or service decommissioning. Last but not least, we have looked at assurance processes. These processes ensure that an end-to-end service instance is free of issues. We call this end-to-end service problem management, and meets its service level. We call this end-to-end service quality management. And somehow we need to link fulfillment and assurance because we have to set up and tear down assurance processes as part of end-to-end service lifecycle management. And all these processes consume management services from the management domains. Let's look at how this this looks in the landscape. So we have here the only process that is in the group of onboarding processes. Here's service design, that is basically out of scope currently. End-to-end service fulfillment includes service instantiation, activation, configuration or reconfiguration, service deactivation, and service decommissioning. And it also has a kind of helper function that keeps the inventory and topology data of the end-to-end service up to date. All these consume the management services. This is depicted here in the middle. And you see here the groups of management services that were introduced in the ZSM architecture. You also see the well-known lollipop and claw notation for service consumption. And yeah, I mean, this is the principle. Management processes consume the management services from the domains. And we also have the assurance column. The assurance column is somewhat linked with the fulfillment column in terms of the instantiation and the decommissioning, because instantiation would need to set up the related service assurance processes, whereas service decommissioning would trigger the tearing down of the assurance for that service instance that is going out of service. All those processes that we saw so far are executed on demand or on request. Whereas we have two processes here that are typically executed continuously, indicated by this little loop icon here, and that's service quality management and service problem management. So here we ensure the SLA is met, and here we ensure that problems are fixed. If this is not possible, we will escalate the problems or the quality issues to a ZSM framework consumer, so to an entity outside the ZSM framework that will then take the responsibility of fixing the issue. I would like to demonstrate one example of a management process, and that is service instantiation. We see here that this is initiated by a request from a ZSM framework consumer, so an entity outside the ZSM framework. And the end-to-end service management domain is responsible for executing this management process. It has access to data stores that could be part of the end-to-end domain, or it could also be part of the common data services or cross-domain data services. And we have the management domains which expose the management services. And this arrow is basically indicates the consumption of a management service by the service consumer, and that's the service producer. So to start the process, the end-to-end service management domain has to retrieve the related data from the service catalog. The service catalog in ZSM also includes information how to manage and to orchestrate the service, so all the templates, service model, and so on. Then it is necessary to determine the policies and KPIs and to obtain information about the inventory and topology. Based on all this, the end-to-end service management domain would understand which are the domain services from which the end-to-end service is composed. It would loop through a subset of those that require a feasibility check and would request from the management domains to perform that feasibility check. So this is the first management service that we will look at between the end-to-end service management domain and the management domains. Based on that, it can be determined if it is feasible to instantiate the end-to-end service. If that is the case, then for every domain service instance that contributes to the end-to-end service, the end-to-end service management domain would either have to request from the management domain the creation of a new domain service instance, or it would have to reuse an existing domain service instance, which it would then share with another end-to-end service instance. In that case, typically the domain service instance needs to be scaled to increase the capacity to cater now for the other service as well. And we have then also a configuration step, typically of all the domain service instances. Finally, the end-to-end service instance is configured. Then we have optionally the possibility to test a set of domain service instances that support it, also run a test on the end-to-end service instance. And once all this is working, we set up the assurance. That means we trigger the collection of performance and fault information related to the domain service instances that we consume for the end-to-end service. And we have to update the end-to-end inventory, considering events that happen inside the end-to-end service management domain, and also information coming from the underlying management domains. So this was one example of such a management process. And let's now go to the second step of ZSM 008. That is the analysis of northbound interface of technology domains and their mapping to the ZSM services that we have collected here. So this is a simplified view of a possible deployment of the architecture. So I'm omitting the integration fabric, as you can see, which is implicitly there, of course. The ZSM Framework consumers consume services that are produced by the end-to-end service management domain. For instance, a service to instantiate a new end-to-end service. For that, we have different technology domains: radio access, fixed access, transport, and core, and cloud. And for each of these technology domains, there is typically a set of standards available from, mostly one standards body. So RAN and core, this is typically done by 3GPP. Fixed access is coming from BBF, but they have a lot of TMF stuff also that they include. And IETF is producing specifications for the transport, and at the NFV is producing specifications for cloud management domain. So what we basically do is we analyze the specifications of these organizations, and we map them to the management services that we have basically collected when defining the management processes. So this set of management services is mapped to the different domains, and of course we also identify gaps. And this is an example how it could look like. This is the fault event service from the domain data collection group, and it has two capabilities: configure monitoring and provide notifications. This is an example how this is done based on 3GPP specifications. In 3GPP, everything is configured using a general provisioning service. So 3GPP SA5 is pretty well following the service-based principles that we have also in ZSM. And we have some functions to, or some capabilities of the 3GPP management services to send the alarms. All this is defined in the ZSM 008 specification. This is work in progress. Step one, the definition of the management processes is basically finished. Some bug fixing is going on. Step two, the mapping is progressing, and we foresee stable draft by the end of this year. Stable draft means it's basically content complete with a small number of known issues and known gaps. That means we would probably be able to publish in early spring next year. You can watch us working on the specification. Here is the URI of the open area of ZSM, where all drafts are provided to the public for review. This again brings me to the end of my second presentation. I was introducing the ZSM 008 specification to you, which defines how to manage the life cycle of cross-domain end-to-end services based on the ZSM Framework reference architecture. ZSM 008 has two main parts or steps. The first one identifies management processes for the onboarding, fulfillment, and assurance, which are built from the ZSM management services. And step two maps the involved management services to the northbound interfaces of different technology domains, namely radio access, fixed access, core, transport and cloud. Yeah, this brings me to the end of my talk, and I'm handing now back to Nurit.
Thank you, Uwe, for this presentation. And I just want to hand over to Zulan, the rapporteur of ZSM 003, that will present us and introduce the end-to-end management and orchestration of network slicing. So Zulan, please.
Okay, hello everybody. I hope you can hear me well. So this is Zolan. I'm the rapporteur of ZSM 003 end-to-end network slicing. Today I'd like to give a brief introduction of ZSM 003. Okay, so ZSM 003 is published in June this year. The objective of ZSM 003 is to specify the end-to-end zero-touch management solution and management interface for end-to-end network slicing. As you may know, network slice is a hot topic discussed in many different standard groups. How to connect the different pieces of the work and build an end-to-end solution is very critical to ensure the realization of network slice. So there are following aspects I would like to introduce today. The first is end-to-end network slice concept, and then typical scenarios and roles for the end-to-end network slicing, end-to-end network slicing management architecture. And I will also share some example of end-to-end network slicing solution procedures, and also talk about the support to the verticals, collaboration of ZSM and the other groups. So there are two major categories of ZSM scenarios which are related to the end-to-end network slicing, which has been specified in ZSM 001. The first category is end-to-end network and service management, which mainly address the automation of end-to-end life cycle management. And the second category is the network as a service. It focuses on the need for the service capability exposure from all domains to enable zero-touch automation. And there are three basic concepts which are related to the end-to-end network slicing. The network slice subnet, and end-to-end network slicing is as defined in 3GPP. So they share the same 3GPP definitions, and end-to-end network slicing concept is specified in ZSM to describe set of management and orchestration activity that allow the deployment and operation of network slice across multiple management domains. Okay, so there are several roles has been involved in the network slicing. So in 5G network, 3GPP has specified 6 roles which are related to the network slice. For example, communication service customer, communication service producer, provider, and network operator, network equipment provider, and some service provider for the virtualization infrastructure. The ZSM Framework consumer plays a role of communication service customer and uses the communication service provided by communication service provider. And there are 2 major scenarios related to the network slice. First, we call it network slice as NOP internal. So in this case, the network slice instance are not visible to the CSC. The business entity X, as we shown in the diagram, take the role of both NOP and CSP, and they deliver the communication service to the vertical customers. The entity X decide whether they use the network slice instance or they use the network to support the communication service. In this case, only the communication service is exposed to the vertical customer. This scenario allows the vertical consumer CSC to use the communication service and monitor the communication service status and also the network performance data where the exposure interfaces. So this is one case. The second scenario is called NSAAS, Network Slice as a Service. In this scenario, allows the vertical customer to use the network slice instance, and optionally they allow the vertical to manage the network slice instance where the management exposure interface. In addition, the vertical can also offer their own communication service on top of the network slice instance. So the end-to-end network slicing adopts the generic architecture specified in ZSM 02, as we already introduced just now. In this diagram, you can see we show the ZSM architecture deployment example for the network slice management. So in the diagram, you can see we have the E2E service management domain, and also we have the corresponding AN management domain, CN management domain, and TN management domain, which supports the end-to-end network slicing. Now let's take a look at the network slicing related solutions. So the first one we call this a life cycle management of the network slice. The life cycle management of network slice contains 4 phases for preparation, commissioning, operation, and decommissioning. So for each phase has their related steps. For example, for the operation, in the operation phase, operator may activate, modify, or deactivate the network slice instance. As an example of provisioning the network slice in the NSAAS scenario, so you can see from the diagram, the first step is the ZSM Framework consumers will send a NSI allocation request to the E2E service MD. And then the E2E service MD distributed the request to the different management domains to follow the provisioning process. In particular, for the provisioning of coordination with transport domains, so the ZSM framework shall be able to differentiate the different transport types, for example, IP network or optical networks, according to the different scenarios. And then it communicates to the corresponding transport management system with the transport requirements. So in 3GPP, they have recognized the following 4 categories of transport requirements, like topology requirements, or latency requirements, bandwidth requirements, or isolation requirements. So this information will be transmitted to the related transport domain for further modification. For the performance management of end-to-end network slice, so there are 2 available performance management reporting mechanisms so far defined in the specification. So the first is performance data file reporting management service. Another one is called performance data streaming management service. Related with the different reporting mechanism, so there also have some related end-to-end KPI and performance measurement specified. So there are 3 categories of performance measurements defined in the specification. So the first category is a KPI for the end-to-end network and service. So it's more regarding the service level KPIs. And the second is more about network slice and network slice subnet related KPI or performance measurements. And the third category is the performance measurements related to the SNSAI. So another features about the fault management for the end-to-end network slicing solutions is similar like the performance. So there are 2 mechanisms to get the fault information. The first one is end-to-end network slice fault notification. Another is you can get end-to-end network slice alarm list. So for the similar situation like the fault notification is the ZSM Framework consumer will decide to subscribe the fault reporting, and the end-to-end service domain will collect the notification from different domain-specific information, fault information, and also convert it to the fault information related to the communication service. So if I move on to the next one is the topology service. For the end-to-end service topology information, service producer will provide the information about the topology of end-to-end network slice. It's also collecting the topology information from the related domains and make it summarized and provided to the end-to-end consumer. So another aspect for the network slicing is we need to talk about how they support to the different verticals. So from the requirement for the network slicing, GSMA has provided information that capturing service requirements for network slice in GST and NEST. The GST is called generic network slice template. Is defined as a set of attributes that can characterize a type of network slice or service. The value of each attribute is assigned to express a set of requirements to support a network slice. The NEST is a GST filled with values. The NEST can be used as input to the network slice preparation. The GST attributes can be classified into two main categories. The first category is character attributes. For example, the KPI, the key performance indicators supported by the network slice, could be belonging to these character attributes. And the second category is the scalability attributes, which provide information about the scalability of the network slice. Taking the GSMA, GST, and NEST as input, some translation work is needed to convert the GST, NEST to the SLS. The SLS carries a set of service level requirements to be satisfied by a network slice. And the end-to-end service management domain is responsible for the further translation of service profile to the corresponding domain requirements and distributed to the related domains as shown in the diagrams. So there are also some examples of service requirement attributes specified in the service profile. A typical example of support vertical is to provide management exposure to the vertical customers. So management of non-public network is an example of using network slicing. In the NOP internal NPN scenario, the vertical customers provide the communication service related SLA requirements to the operators. So in this case, the slice information is invisible to the vertical customers. In the NSAS NPN scenario, a dedicated network slice can be offered to a vertical as a service. In this case, vertical could use the provided network slice instance and manage it. Okay, so as you can see from the previous introduction, the implementation of end-to-end network slicing involves many different parties. The responsibility of ZSM is to stitch the work from different groups and provide a federated solution. The end-to-end management domain of the ZSM framework coordinates with the underlying management domains from each of the technical fields and also support to the vertical customer requests with end-to-end network slice. Okay, so for the next step for the end-to-end network slicing, we think with the autonomous network discussion recently in the industry, we believe that some studies on the autonomous aspect for the end-to-end network slicing is needed. For example, for the study relation with the intent-driven management and how to use the closed loop automation in the network slicing scenarios are very important, maybe for the further study. And we also welcome the new POCs based on the ZSM 003 work to be carried on in the following phase 3 work. Okay, so that concludes my presentation. Thank you.
Thank you, Zola, for the presentation and also for the call for the POC. This is, of course, a very important aspect to demonstrate the viability of the technology, and we welcome the industry players to join us and to demonstrate that via POCs. Anyone is invited to do that. You don't need to necessarily be an ETSI member and do that. In doing that, just connect with one partner from a ZSM member, and you can do that. Okay, another aspect that relates to the end-to-end solution is, of course, the automation of the CICD for ZSM services and managed services. And I would like to invite the rapporteur of ZSM 13, Ishan Vaishnavi, to present. So Ishan, please.
Can you hear me?
Yes.
Good. So yeah, good morning to everyone. Happy to be presenting here on the CICD topic. Let's get started. This is a new work that we started, and the reason for starting this work was essentially realizing that basically, so on the right, we have this complicated picture about management domains and the end-to-end management domains and the sort of layers that we would have. And we start to realize that almost all of the layers are in software. So essentially, a large part of the management domain is software. Not only that, the whole infrastructure is getting extremely complex, and increasingly end-to-end services and network slices that we saw the presentations from Uwe and Zulan from can be dynamically created and removed from the network. And this naturally means that since they can be dynamically created and removed, that operators would eventually want newer network slices with newer features, shorter release times, things like that. This naturally leads to issues with software management. So we want to move to an objective where we have more automated software update and a management cycle. This naturally leads to CI/CD. And in this talk, we will just look at the challenges that we are going to solve in this work. Since this work has just started, we don't have, let's say we don't have fully developed solutions, and most of them are under discussion. So here is a little background on CI/CD. So you have a basic CI/CD pipeline where you do some kind of coding, you do some initial testing. At the vendor location, this could be using an internal CI/CD pipeline. And then you package that and you deliver it to an operator. The operator then picks it up and can validate it and then do its own internal testing. And then if everything goes through, it deploys that in an operational environment. And the unique feature or the unique issue or aspect that we need to address in ZSM is that we are in telecommunications. And that means that there is not a single vendor. Each vendor has a different CI/CD pipeline and probably different providers to implement that. Therefore, we need to be able to somehow manage the software that is delivered from different vendors using different pipelines to a common pipeline. And we want to automate this entire process across multiple domains. What we notice is that we really cannot influence the internal testing itself. So we cannot go in and change the processes that the operator has for testing. What we can do is sort of address the pipeline and address the interfaces or the management services that we need to be able to perform this testing or to be able to change how this testing is performed. So the question that we are trying to answer is, how is this automation done in a multi-domain environment? and we look at some, let's say, challenges that we are going to address in the next year. So to map this architecture or this process into the ZSM architecture, it would look something like this. Let's assume in this deployment that we have each domain provided by a different vendor. Each vendor, after its own internal testing, provides us with the software. The operator performs joint testing, and this software is delivered to individual domains. So let's say there is a 3GPP domain or an HCNFE domain or a RAN domain, and that is provided by different vendors. And the end-to-end operator domain should be able to manage all these domains and all these tests. So what are basically tests? So we classify tests in basically the following types. On the left, you see what we call pre-test. These are standard CICD tests, so unit tests, where you individually test each piece of software without its interaction with the system. Integration tests, where you basically test the software while it's interacting with one or two more pieces of software, so a limited set. And system sets, where you see how the software performs in the entire system. And furthermore, what we are also interested in here is in operational tests, which means some kind of simulated tests, so simulating the environment, and rollout tests, so that while you're rolling out the software into production or operation, you're also performing tests at the same time. So this part from now on is more or less under discussion. So it is subject to small changes. So the first challenge that we want to, let's say, address is that we need to test across domains. So testing within a domain, let's say, could be handled by 3GPP alone or by HCNFE alone. The point of ZSM is to be able to stitch those domains together. So therefore, we need to be able to test across those domains. So let's say you have a new piece of software. So NS stands for new software. That has been delivered for domain X, and it has passed all internal testing. You want to make sure how this new software works with the old software that exists in another domain, for example, in the end-to-end service domain. So the challenges in this part are that you need to ensure that the new software works with the old software from a different domain. And this you need first to be incorporated in the operator internal testing part itself. So you need to have some kind of integration as well as system test for this. Additionally, you want to be able to test this in operations. So this is the first challenge that we want to do. So there are a couple of small aspects of this challenge shown here. The second challenge that we have is that the management services that we are speaking about, that's the lollipop that Uwe introduced, is also software, right? So this management service is also subject to bugs and is also subject to updates through the CICD pipeline. How do you test for that? So far, in the previous slide, we were testing for the end-to-end service itself. So new piece of software that is delivered into a domain to be tested. But how do you test for the management service itself? Because let's say you have a provisioning management service that has been updated. If the new one doesn't work, it is very difficult to continue to work with the domain because you've basically ended up disconnecting the domain. So you need a mechanism to test for the new management service without actually disconnecting the domain from the whole ZSM framework. So that's the second challenge. And the third one that we want to look into are simulated tests. What that means is that you have an operational environment and you have a piece of an old software in the operational environment. And what you can do is you can take a sort of copy of the old software of the entire system, And this is sort of a digital twin or a simulated twin environment which is constantly updated based on the occurrences in the network. And you can replace the old software in this simulated or twin environment with the new software and test it in the twin itself. So this is what we mean by simulated tests. So basically testing in a simulation of the entire system. How to do this is under discussion because this has some requirements, some data collection requirements on the, let's say, operational environment that we need to support. And finally, the next challenge is rollout tests. So let's say the operator internal testing is passed and the new piece of software can be delivered and deployed into the domain. What we would like to do now is to develop the operator confidence in this new piece of software without causing major issues. And we know that tests don't capture everything, right? So we know tests could miss some issues and operation is always different from the test. So what we thought of is a rollout testing, where basically the consumers that are using the old piece of software are slowly migrated towards the new piece of software. And once that's completely finished, what you can do is, if everything works well, just remove the old piece of software. So this is what we mean by rollout testing. So in this way, what happens is basically you don't get the network into an error state, and the operator can do this rollout slowly while testing the new software. So what are the takeaways? So this is a study. So it's let's say the start of work for this study, and we have so far identified 4 challenges that we presented. First and foremost is the multi-domain automated tests for the end-to-end service across domains, the testing of the management service itself, simulated testing, as well as rollout testing. So all these aspects are currently under discussion, and we hope to see in the next year, let's say, even more challenges, even more scenarios that we will address in the study item. Thank you. I hand it back to you.
Thank you, Ishan, for the introduction of the study. And now we actually reached the point that we want to start about key automation technologies. One of the roles of the ZSM group is to define or specify key automation technologies that should be leveraged by the different organizations in the industry to ensure that we have alignment, that we leverage synergies, that we can enable end-to-end and achieve end-to-end automation, and ensure that we have cross-domain, cross-plane, cross-layer, cross-use cases, coherent operations across the network. And we will start with the first one, and I would like to invite Magnus Borgård from Ericsson, the rapporteur of ZSM 011, that he will talk about the intent-driven autonomous network study that he's heading, and he's the rapporteur. Magnus, please.
Yeah, thank you, Nurit. I hope you can hear me well.
Yeah, we can hear you.
And so welcome everyone to this presentation on the intent-driven autonomous networks. So let me start with some introduction and definition of intent. There is work on intent in many other standardization organizations. So this definition is sort of a joint definition from ZSM, also in 3GPP, and then TM Forum has the same or similar definition. So intent is the formal specification of all expectations, including requirements, goals, and constraints given to a technical system. So let's look at that more. So from a user perspective, it expresses the what the system is expected to achieve. It all includes all the system needs to know goals, requirements, constraints, and so on. It needs formal modeling and common semantics to be understandable to the system. It is not only used on the human-machine interface, but in internal goal setting between subsystems. And the natural language and other domain-specific languages can be used, but it requires local interpretation and translation into the common intent model. And the request to fulfill the intent has its life cycle actively managed by the intent owner, the creator, sender, through the intent API. So the intent owner is the one that is in charge of the life cycle. Let us look a bit more at the general properties of intents. There are declarative goals and utility. So declarative instead of imperative, leaving its implementation open. And ideally, an expression of utility. And you can see here, utility is sort of expressed as the total satisfaction received from consuming a good or service. And it comes actually from a term in economics, where it's based on rational choice that usually assume that consumers will strive to maximize their subjective utility. So it's actually up to the consumer to judge whether this utility is correct. And infrastructure and agnostic and portable. So it's not device nor infrastructure specific. It's adaptive to user expectations, constraints, and changing requirements, but decoupled from variations in the underlying infrastructure. It's portable across platforms, vendors, implementations, ideally. It's composable and additive, so multiple intents may be given to a system independently. And the system is expected to consider them all together, even if they may be sort of contradicting. Complete and exhaustive intent is describing all expectations comprehensively. And if a requirement or concern is not described by intent, it is not recognized as required or relevant. There is no sort of such thing as common sense here, and you have to express everything. It's persistent. It is a knowledge object with actively managed lifecycle, and intent stays valid until it's actively removed. Let's just look at this use case to get the feel of this. This is a use case that is described in the work item. It's the TerraFlow automotive use case scenario. So TerraFlow is a European Union funded project. It's for smart connectivity beyond 5G. And it's talking about CCAM applications, cooperative, connected, and automated mobility. So it's looking for low latency, high capacity, and massive flow management. And you can see here by the picture here that it's looking for sort of handling information and solutions over sort of in this case, a traffic situation. So the main KPIs are resource sufficiency, multi-tenancy support, latency, trust and privacy, and OPEX reduction. So these KPIs are both technical and business oriented. And the reason for why this is a use case in our intent work item, is that these KPIs can be represented as intents. And provided by automotive verticals that has no sense of how it's going to be fulfilled. So it can be sent to the customer-facing service portal. So that could be, for instance, the TerraFlow open source here, or other CSP's portal. And this is typically that you can use the ZSM framework to construct this. It's important to transform intents into RAN domain intents and core network domains, MEC domain intents, or transport domain intents. And this is typically a good match to then the ZSM architecture, where the whole idea is to be able to sort of work together between different domains. And the capabilities are intent decomposition and assurance. Okay, so let's take a look here at the connection to the ZSM framework. You heard Uwe earlier today talk about the architecture, and actually in the architecture specification, we have something called support of intent-based interfaces, and that's actually part of the domain orchestration. So it's already sort of prepared for introducing intent. Intent principles in CSM. So an intent typically emanates from a service or network customer, but can also have another source. That can be, for instance, a network function or another intent. And typically, we see that the intents seem to be sort of built-in hierarchies, where you have an original intent that makes sense from the sender of the intent, and then it's sort of translated into new context and to make it sort of understandable by other domains. So an intent provides guidance to an autonomous network regarding expectation from the source on service or network behavior. An intent has a separate life cycle, and a zero-touch network could be based exclusively on intents in principle, but a mixed scenario where intent complements service-based management is more likely. And about the life cycle, of course, the network and services and so on can have a different life cycle, but the intent is then a life cycle controlled by the intent owner. So let's move on. So what are is it the direction of the intent-driven automation study in CSM? The ZSM framework is getting traction. So as a clean, straightforward description of a service-based architecture for zero-touch automated network and service management in a multi-vendor environment. And the concept of intent-driven management is being revived as a key ingredient for autonomous networks and zero-touch operation. It has been sort of discussed in research and industry back and forth, and now it seems to be at a new peak of interest. So several standards bodies and open source projects have initiated new work items, and the study will take the progress of those combined with prior work. So the purpose is to make intent-driven interactions feasible in CSM and fill gaps in the industry. The main task is to investigate and suggest ways to enrich CSM service-based reference architecture with the possibility to receive, transform, convey, and act upon intents. And the study will provide guidelines on how to use intent-driven management interfaces and to outline recommendation of needed capabilities for intent-driven management within the CSM framework. And the result from the study will become a basis for a new normative specification. And we've been working on this study for well, almost a year now. And I think that it has shown that it is a rather complex area, and we have a good discussion. We're not always sort of immediately aligned on what we think, but I think it's a very interesting area. So I should also say that the ZSM service-based reference architecture sort of serves as a guide here to sort it out. There has been a lot of work in TM Forum on autonomous network and the intent there. And we can see a resemblance. We can see that there is a possibility to map the hierarchy that has been sort of described in TM Forum to the ZSM architecture. So that's good. And in TM Forum, there's been a evolution of concept of intent handling function, which is sort of a centerpiece in their description of how you sort of transmit and transform intents throughout a hierarchy of intents. And they have introduced an architecture of intent handling built from these functions. In ZSM, we don't sort of standardize this kind of handling functions or this type of artifact. So we are looking at the interfaces, but we do have our own interpretation of this logical entity, and we'll look at that now. So we call it the intent management entity. So it is a logical entity that we assume are in place in the different domains, and where the sort of intents can be received, can be sort of analyzed, and actions can be sent, and new intents can be created and sent to other intent management entities. But again, it's the interfaces between the domains that is our intention to standardize. If we look at the sort of mapping of intent handling entities into the ZSM architecture, you can see typically that there will be an intent management entity at the ZSM Framework consumer layer, and there is typically sort of an intent owner and a certain utility that is wanted by a consumer. And then that is sent to the intent management entity in the end-to-end service domain, management domain, over the end-to-end intent handling interface, which is actually part of the end-to-end orchestration, but I've separated it out here for the purpose of this description. And then the intent management entity will then decide which services to engage and which sort of intent that should be sent to the underlying domains. And that you see at the bottom here, the management domains have this entity, and there could also be an intent management entity at the network resource level. So the idea here is that we will have intents being transmitted in the between the end-to-end and the the management domains, but we will also see a mix of using services that are available and sending intents down in the system. Here is a picture from an 3GPP that is also working with intent. And you can see here that there is an interworking between the control loop and the intent. So typically an intent is depending on this kind of closed loops. So you can see at the top, the intent owner is the management service consumer, will send an intent and get feedback from the intent handler, which is the intent, the management service producer, and that will become a feedback loop, closed loop, and then there is another loop from the sort of intent handler to the managed entities. So the intent-driven management make use of a closed loop to continuously monitor intent fulfillment. So if we look at the standardization needs across the different SDOs, there is the concepts around intent, the definition of intent. You saw that before in the operation principles. And we come from different angles, but I think there is a good work in trying to align this, and CSM has an important role there. Intent modeling, a formal definition of intent and reports, model federation allowing domain-specific extensions by SDOs and vendors. And the idea here is that each SDO should be able to define its own model for its specific domain, but that it would be possible to federate these different models so that you can follow the intent from the top down to the different domains. There is the intent interface API that we've been talking a lot about, intent owner and intent handler. And that also means that you have this management service producer and management service consumer that will have to be defined here in the interface. Lifecycle management, negotiation, and feasibility. So you have to find out whether the intent handler can actually handle the intent. The intent handler's capability, registration, and discovery, and interface is domain agnostic, as I said before, and highly reusable. And then there is the intent lifecycle, role definitions, owners and handler, and phases in the lifecycle. So in summary, the intent aims as a specification of what the system is expected to achieve instead of providing instructions on how it should be done. And the intent-driven automation is a hot topic in many SDOs and open source projects. And the ZSM work items started a year ago, and the focus is intent as key enabler for autonomous networks, end-to-end aspects between domains, and conflict handling. And the outcomes are recommendations on needed capabilities, interfaces, lifecycle management, inventory, knowledge management, etc. Publication is planned for early next year, and the results from the study is intended as a basis for a new normative specification. So thank you very much for your attention, and please give any feedback, comments, as you please. Here is my email address. Thank you very much. And back to you, Nurit.
Thank you, Magnus, for the very interesting presentation, and we look forward to see this study concluded and normative specification to be started and leverage across the industry to ensure that we have a consistent way how to provide the intent across the networks to attract the use of the intent-based interfaces and also to attract the developers to use that. Now you touched also the closed loop automation, and with this I would like to switch to the next key automation technology, which is about closed loop, or the enablers, the solutions, the advanced topics, and to highlight why it is so important that the industry leverage this key automation technology and ensure alignment with it. So I would like to invite here three presenters that will split the time between themselves. Pedro Gomes from Ericsson, which is the rapporteur of the closed loop automation enablers. Ishan again, that is the rapporteur of the closed loop automation solutions, and Laurent from Architecture, that is the rapporteur of the ZSM closed loop advanced topics, which is the study with more advanced topics for closed loop. So please. So who is starting? Is it Laurent? We cannot hear you.
Sorry, I was muted. Sorry. All right, can you hear me now?
Yes, Ishan.
All right, so let's start again. So unfortunately, Pedro is not able to join us for personal reasons, but very understandable personal reasons. But me and Laurent will take care of the slides. So this is a joint, let's say, work in two work items and one study item, which Pedro, myself, and Laurent are responsible for. So the ZSM 9.1 is 100% completed and has been published, and that is the one that Pedro is responsible for. It talks about the closed loop enablers. 9.2 talks about solutions to automation scenarios, and that is the one I'm responsible for. And 9.3 talks about advanced topics and future work. So the way we've organized the presentation is essentially we look into basic closed loop concepts. I will go through them quickly because Uwe and other presenters already introduced them. Then the automation scenarios and solutions. These are primarily a combination of 9.2 and 9.1. 9.2 presents the scenarios and solution, and 9.1 the enablers that are used in those solutions. Then we go into future work with Laurent will present, and then we look into adoption in other groups. So let's get started. Basics of closed loop. Well, we firstly, what is the objective of this work is essentially automation. The primary enabler for automation is closed loops, right? So we wanted to go into the details of closed loop to see how they work, how we can use them, what kind of features do we have, do they need to have. And essentially that means that we are going to specify management services for closed loop integration, and that basically bind closed loops from different vendors in an operator network. And how do we solve key automation scenarios using closed loops? So that's the basic objective. And since we are in a zero-touch group or an automation group, we wanted to lead the community in this talk. So those were the objectives of this 3 work. But this is the, let's say, an introduction to closed loop. I think Uwe already mentioned this. So we have a basic concept of, and this is a MAPE-K loop. So you have a basic managed entity, you monitor the managed entity, you receive some data from it, and you analyze the data, and you decide based on that analysis on if you want to change something and what do you want to change, and that you execute that decision. And in a MAPE-K loop, the knowledge that is gained from all these steps is then stored into a common knowledge store. So this is the functional view of a closed loop, but as we will see, this has changed based on our work. And how does this apply in the ZSM framework? The red circles here represent the closed loops. So you have closed loops within the end-to-end management domain, and you have closed loops at each management domain. Furthermore, you have basically the management services from the management domains to the integration fabric, and then also from the end-to-end management domain to the integration fabric that help all those closed loops to speak to each other. Additionally, you can have closed loops across domains as well. And so what we, let's say, specified are enablers for closed loop governance and closed loop coordination primarily. And then there are some additional enablers that help integrate those closed loops. Going forward, and then now we look into some scenarios and how do we automate those with closed loops, and what are the enablers that we require for those. The first and foremost need that we have is to uniformly manage closed loops from different vendors. So we have, let's say, 3 different vendors, 3 different management domains, and each vendor provides us with a closed loop of their own implementation. The operator's end-to-end domain needs to be able to integrate those closed loops together with the closed loop that the end-to-end domain itself has. So we need to be able to manage them uniformly. That is the first and foremost requirement that we have, to be able to stitch some different domains together. What does this mean? So the basic enablers for doing that, we have the closed loop governance management service, and that can essentially do a lifecycle management of the closed loop. So you can disable or enable closed loops, or as you will see later, do some more advanced operations with closed loops. You may be able to configure the goal of the closed loop that the closed loop wants to achieve. So whether it is to optimize some KPI or it is to reduce energy consumption, for example. And additionally, you may be able to escalate and delegate between domains. What does escalate and delegate mean? Basically, the closed loop at the end-to-end domain should be able to delegate a part of its goal to a closed loop in a management domain. And a closed loop in a management domain may need to escalate some issues that it may detect to the end-to-end domain. So we have management services for those. Additionally, we also said that one domain may need to cooperate with another management domain to achieve some common objectives. So for example, if the end-to-end service exists between those two domains, across those two domains, then the closed loop in one domain needs to cooperate with the closed loop in another domain to ensure that correct decisions are being taken. And finally, to manage a closed loop uniformly across domains, you need to have a common understanding of what a closed loop is. So you need to have an understanding of the life cycle of a closed loop. So we here say there is the preparation phase, the commissioning phase, the operation phase, and the decommissioning phase. In the operation phase, the closed loop may be activated, deactivated, monitored, evaluated, or upgraded. So this is the lifecycle phase. And then we developed a closed loop model. So this is very high level. There are further details if you look into ZSM 0091. We developed closed loop model, which basically can have one or more closed loop goals, which need to be optimized. One or more managed entities. So the entity that the closed loop is trying to optimize, so manage. And closed loop components. Closed loop components are the stages as well as the that make the closed loop, including the knowledge. That's why they're called components. So this is essentially the basics of how to manage closed loops. And most of this work has been specified in ZSM 0091. Then we go into particular scenarios. One of the first scenario is to be able to coordinate closed loops. So the need for coordination comes from the fact that we are going to have different consumers that sort of will deploy different end-to-end services. And these end-to-end services are in the current infrastructure in a virtual layer. But that virtual layer is shared over this common physical infrastructure. And inevitably, this will lead to conflicts. So service 1 would want to do something else with the physical infrastructure, while service 2 would want to do something else. And so closed loop would need to be able to manage these conflicts. And an analysis on the type of conflicts that we did was basically that you can have conflicts in the metrics. So what is that you want to optimize? Or you can have parameter conflicts. So that closed loop 1 is trying to change a parameter, that closed loop X is also trying to change at the same time. Additionally, we did further analysis to identify more conflicts where, so as I said here, you have conflicts at the level of setting the goal of the closed loop. Then you may have conflicts when a decision stage outputs certain decisions or action plans, as we call them in ZSM. Those decisions or action plans may conflict. So let's say while one closed loop is trying to optimize user experience, the other one is trying to reduce energy consumption, thereby reducing user experience. So these may conflict at the decision stage. Finally, there may be conflicts at the action stage. So the actions that you're actually trying to execute on the managed entities. And finally, what you need to do is once those actions have been executed, they need to be coordinated in some way. So that's a part of concurrency coordination. And after execution, you need to assess the impact there. So what the solutions we came up with are primarily for, firstly, for after the decision stage. What we say is that for each closed loop, we may identify a set of decisions that the closed loop cannot take. So we disable those decisions for them. And this is done by the pre-execution coordination service. So basically, it can provide notifications for conflicting actions and can get recommended action plans. So using that, you may be able to disable certain actions or evaluate the results of actions or suggest different actions. The same thing could also be done after the execution stage. So you can disable a set of actions that the closed loop is taking. And this is done by the post-execution coordination service. Going forward, so now is the part of detecting goal conflicts. So let's say there is a domain X with multiple closed loop, each with its own goal that's already running. And a new consumer comes in and says, I would like to install a new closed loop with the following goal. Before you can instantiate this and activate this closed loop, the goal is checked with existing goals if they conflict. And if they don't conflict, then it's fine. If they conflict, then a notification is sent to the consumer. This is done by the capability called goal feasibility check. Basically, it checks if the goal can be supported by the end-to-end MD, and you may specify a timeout for this check. So this is about coordinating closed loops and detecting conflicts. The next scenario that we go into is need for trust in closed loops. So essentially what happens is an operator may buy these domains from different vendors, and the vendor have their own implementation of closed loops. But the point is that these closed loops will actually configure the operator network. So they will issue network configurations. So the operator needs to be able to trust these closed loops to let them run in its own network. One way of establishing trust is to give complete control to the operator. And that's done by modeling the closed loop as a managed entity, which means that closed loop is just like any other managed entity. So you can do lifecycle create, update, delete operations on closed loop. So you can basically disable a closed loop if you don't like it. You could get performance and usage metrics like you can get on any other managed entity. And you can run a closed loop on a closed loop. So this enables the integration of closed loops together with other closed loops. But disabling a closed loop or managing a closed loop is not enough. So we went into a bit more details. Let's say we came up with another solution that we call is pause and review of a closed loop. So what happens here is that, so this is the closed loop execution stage that is going to configure the network. And let's say this is an example configuration of increased DNF resource for network function 1. Is the configuration that it's giving to the network, and so the network increases the DNF resource for network function 1. Well, if the operator is not sure about this configuration, what the operator could first do is pause any changes for NF1. So it can say that for this closed loop, any changes that it issues to NF1, I would need to review them first, which breaks this connection. And what happens now is that if you get a request to increase DNF resources from NF1 from the closed loop, a notification is sent to the operator saying the pause point has been reached, and the operator needs to review the actions that the closed loop is taking and then send an approval for resuming the closed loop. So what this does is basically essentially every time an action is being taken that the operator has paused, the operator gets to review them. Once the operator trusts the operation of the closed loop saying, okay, this closed loop seems to do the right things, it can disable the pause point and the closed loop executes normally. The final scenario is in relation to autonomicity, not automation. It's that you can let the whole system run on its own. And the point here, the graph I'm trying to show is the hourly traffic by device at different times during the day. And you see the more important aspect is the time and the usage of the network. So the network does different things, has different requirements at different times. So an automation system that is trying to automate this network cannot be doing the same thing at midnight, at noon, at 6 p.m. It cannot have the same goals. It must have different goals at different times. And if you want to let the system run in an autonomic fashion, that there is no user interaction, we need to add that feature to closed loops. So closed loops, this essentially means the closed loops cannot optimize for the same goal the whole day. So one of the solutions that we have for this is what we call condition-based goal change. So an example here is that when the condition is met, the closed loop must minimize energy. Otherwise, if the condition is not met, it may maximize quality of experience. And the condition could be anything. So it could be not just the time of the day, it could be any KPIs that you measure in the network and so on. So how this would work is basically the condition is set in the network. So it says, so there is a management services that allows you to set a condition and the corresponding goal, change of goals. So there is a condition listener in the network that then notifies if the management service producer, if the condition is reached. And what the management service producer essentially then does is change the goal of the closed loop. So this does not require any human involvement. So it's completely autonomic change of goal based on certain conditions in the network. The other solution that we could have is actually not changing the goal, but changing the closed loop itself. So the same thing happens. You set the condition to goal association, the event and condition listener fires. But instead of changing the goal of a closed loop, it deactivates an existing closed loop and activates a new one. Essentially, it has the same effect. So this was about having autonomy in automated operation of closed loops. So if you have enough of these conditions, the network can essentially run the whole day on its own managing its own closed loops. Finally, we have need for customized closed loops. So the point here is different operators may have different requirements. So you have an operator A that has a highly reliable end-to-end service, and the operator really understands the set of things that can fail, and he knows how to solve them. Whereas operator B has a best effort end-to-end service and does not really have an understanding of things that can fail or their solutions. Of course, this means that the requirements on the closed loops are different, because the closed loop here needs to be, since the end-to-end service is highly reliable, the closed loop needs to have a fast response for failures. If there is a failure in the end-to-end service, the closed loop needs to respond fast. The fact that the operator understands all the things that can fail and the solutions well is basically can be used to create a failure to solution mapping based closed loop, which is a policy based closed loop. In this case, where the operator has a best effort end-to-end service, best effort implies that there is no time requirement. So if there is a failure, and the operator cannot take years to fix that failure, but has some time to fix it, doesn't need immediate operations. The fact that he doesn't have a real understanding implies that you cannot have policy-based solutions. You need some kind of analytics in the closed loop to figure out the problems and solutions. And this is what we tried to show here. Well, in this closed loop, for example, you have the monitor stage, a decision stage, and execution stage. So this could be a policy-based fast loop. In addition, in another case, you could have an analytics-based slow loop. So here you don't have policy, but an analytics stage that feeds into the decision. This is the standard closed loop design that we saw. But you could have a hybrid loop where the lower layer closed loop is fast, but the upper layer closed loop analyzes the decisions it's taking and changes those decisions over time. And essentially what this means is closed loops are not always a collection of 4 stages, and closed loop flows may follow different paths. That means a message or a packet that appears here may follow path through this, or may follow path through this, or both. So how do we do this? How do we support this? So we came up with a management service. What it essentially can do is receive closed loop description and requirements. And now we start to go into future work. What it could do is pick a set of stages or components that would then form the closed loop, connect them together into a closed loop, set the goal for the closed loop, activate the closed loop, and return a closed loop identifier. So this is a basic solution of how you could create a closed loop with a set of management services or components that exist in the domain. And different closed loops could then be created for different, let's say, requirements or descriptions. So this is what we call make-to-order closed loops. But there are multiple questions that remain. How do you do the closed loop descriptions? How do you map the CL stages to the requirements in the closed loop description? So this is all left for future work. And I will now hand it over to Laurent to discuss future work.
Hello, everyone. I hope you can hear me well. So I will take over from Ishan here to expose to you the upcoming challenges concerning work on closed loop automation in ZSM. So thanks, Ishan, for introducing a lot of the basis for the things I will present in the next slide. So if you can move on to the next one, please. Yes. So the as you've seen in the slide presented by Ishan, there have been already quite a lot of work done into specifying enablers and solutions for closed loop automation, but there are still open challenges. And so the goal of this study item, which is a 9-3, is really to look into what's left, in fact, to enable a complete next generation AI-powered closed loop operation. And for that, we will be looking into different set of topics, such as how to integrate learning or cognitive capabilities in the closed loop, in the different stages of the closed loop, but also how to set the levels of autonomy or supervision to enable autonomous operation of the closed loop, etc. So there are a number of topics that we will handle as open challenges. And the idea is to propose, to investigate what are the potential solutions available today or foreseen to address those challenges. And then finally, as a conclusion to this report, to highlight recommendation for future work, either in standardization like ZSM or also beyond in terms of addressing the open challenges for closed loop automation. If you go to the next slide, please. So one of the first topics we investigate in this study is the so-called cognitive closed loops. And the general idea is really to, based on what you have seen into the different components that can compose a closed loop in different forms, is really if we introduce, for instance, let's say machine learning capabilities in the different stages of the closed loop. So not only into the analysis stage or the decision stage, but having a broader understanding to say, even if the monitoring stage, for instance, or measurement, if we want to be able to use the ability of machine learning for doing better intelligent probing or predictive understanding of what I will need to measure, in fact, to improve the behavior of the loop or the performance of the loop. These are the kind of topics we investigate in this report to highlight the potential benefits of introducing machine learning or different types of AI technologies as part of the loop, and what are in fact the challenges to make this integration as part of the loop, and how it could be enabled into a multi-vendor environment. If you move on to the next slide, please. So as part of initial, let's say, simple approaches to enable that, there are a bit of a dual aspect that we are proposing here. So what you have at the bottom is, in fact, if you consider, as you have seen maybe in the previous slides from Ishan, you could have, in fact, multiple, let's say, mechanism involved into the closed loop stages. Here, for instance, at the bottom, we concentrate on the analytics models. And you can, in fact, support multiple analytics model or activate different analytics model based on the need that you have, that the closed loop is, in fact, facing the situation it needs to solve. And so these analytics models needs to be able to be activated and deactivated dynamically and based on context. And also you can see what you have next to the analytics model on the left side, that they need to have proper data. You have what we call the regular data sources that this analytics model consumes. And you may have also, based on, again, the context, to generate a data feed coming from on-demand data sources. So you see you have this aspect of activation, deactivation of the proper analytics model. And what you have on the top, which is the dynamic interaction with data sources, is in fact this interplay between the closed loop and understanding what are the right elements, what are the right metrics to collect, to measure, in order to provide the closed loop with the right set of data so that it can define the right context to operate. And you see this is also well linked with the ZSM framework, what Uwe presented in the initial presentation, with having this notion of data services where you want to be able to collect data from different sources. If you move on to the next slide. So still in this context of cognitive closed loops, Ishan showed you a kind of approach where you can have a loop that are not, that can have multiple paths going through the loop, depending on either the speed in which you need to react or the reliability of operation you expect from the loop. So this will essentially consist into what you see on the right side, the so-called operational loop. So you go from monitoring, analyzing the context, defining plans and decision, and then take some actions. And then you monitor, in fact, the impact, the effect of the closed loop actions on the environment. And then what you see on the left side, which is the cognitive loop, is in fact to collect at the level of the closed loop itself, not from an external system, but the loop, in fact, is self-reflective. So it's able to monitor the effect of its own actions, to record this knowledge, as you see a bit in the context-based efficiency and context-based impact, to collect and store this knowledge, these experiences of previous actions, previous execution cycles, and to reuse this knowledge and this kind of, you see you have a kind of internal loop between operational and cognitive loops to, in fact, improve the behavior of the loop by itself. It's a self-improvement, self-learning process, so that you can also, by the loop itself, improve over time the behavior and the effect of this loop. So this is some aspects we investigate concerning cognitive closed loops. And Ishan, if you move to the next slide. Another key domain we investigate in the report, and this is linked to what Magnus presented on ZSM 11 with intent-driven management operation, is in fact that we have many different multiple closed loops that will be deployed at different places or domains in the network. So you have at the bottom, of course, these different management domains that can correspond to different technologies or geographical domains, access, transport, core, etc. And you will have a multitude of closed loop there. But you will have also to keep consistency and let's say coherent operations with the service layer, the end-to-end service management domain that we have seen. So this end-to-end service operation, you will also have different types of closed loop that will in fact use the outcome of the bottom closed loops in their operation. And what you see at the bottom, the first layer, which is label 1, you have here the business impact, the business relationship. And if you remember a bit what Magnus presented, we have those intents that are used as a mechanism, in fact, as interactions between different loops, different entities in ZSM. And here in the closed loop automation, the approach is that there will be intent corresponding to different purposes of the different loops. But there is also this notion, this kind of big loop that you see in a dotted line, that we need to provide consistency when you have different intents. And this will derive into multiple loops, that the overall behavior of all these interacting loops is preserved consistent and using this intent mechanism as a basis for their interactions. So this is also another topic we investigate as an open challenge for closed loop operation, how we can define closed loop based on intents and also drive their operation based on intent. If you go to the next slide. And finally, one of the last key challenge we explore right now, and this is still a work in progress, is in fact what we call the dynamic levels of autonomy and supervision. And here the idea is that when you have closed loop deployed into the network, you delegate, in fact, you remember Ishan mentioned the aspect of escalating and delegating. So you have this delegation of power, this delegation of autonomy. You give authority, you give power to the loop to do some activity on your behalf. But then there is the question of how do you in fact set this autonomy you expect from the loop to do? And it's not only binary. You don't want to say you do everything and I have no visibility. So in fact, what is a bit at the bottom of this slide, we want to go into a kind of, to enable dynamic and conditional activation and deactivation of the closed loop autonomous operation. And here, the challenges or the question that arises are, who decide, in fact, where and when the different tasks are handled either by the closed loop or are kept under the control of a human operator. So when you want to shift, in fact, who is doing what, this autonomy. The other thing is, it's not always uniform. You may have different autonomy or supervision requirements for the different closed loop, or even at the level of a closed loop stage. You may, for instance, if you have a very sophisticated and critical decision-making mechanism, you may set a high level of supervision because you want to be sure that when the decision is reached, you may be able to audit it or to consent to this decision. So you see, you may tune the level of supervision and the level of autonomy according to the different stages based on the criticality also of the action that is performed. And finally, the last point, or challenges or open questions in this aspect of autonomy and supervision is, in fact, the role and the place of the operator. So the operators can use also these levels of autonomy and supervision, or the means to set them, in order to define when and for what he needs or he wants to be kept in the loop. So what information, in fact, shall be reported, if there are any recorded information that should be available for audit, and when, in fact, those information should be brought up to the operator. And yet you have also cases that we investigate, like, for instance, if you want to have if you have a new loop deployed, it's a kind of quarantine mode until you have built enough trust into the operation and the performance of this loop. Or if you have loops that are new again, you may put them into a kind of test mode or validation mode. So you see, you can use this setting of autonomy and supervision level to achieve different expectations. So this is the different topics we investigate as part of the open challenges for closed loop automation. And I think, Ishan, if you move to the next slide, we enter a different aspect we wanted to comment also in this presentation, which is, let's say, our perception of external adoption of work we have done into ZSM on closed-loop automation by other groups. Move on to the next slide, please, Ishan. So, for instance, in ONAP, the Linux Foundation project ONAP, there is an ongoing POC on cross-domain and cross-layer VPN use case supporting closed-loop automation. And you can see on the diagram and the corresponding text that this POC is in fact reusing or leveraging the HC specification about the different components and the logical flow that is used. So, very briefly, so the loop is working in the order, it's counterclockwise with respect to what we have seen before. So you have to go from left to right and down to up. But if you start at the bottom left, you have the SDN controller that in fact constitutes the monitor to analyze this flow or part of the closed loop, which receive and collect telemetry data and move it on to the ONAP component DCAA, which is responsible for analysis. And then you have the second step of this flow, the A to D analysis, which is in fact going from analysis to decision. So the DCAA performs data analytics on the received data changes and generate and sends the data insights to the policy. So the policy block here that you see will correspond in HC's ZSM specification to the decision stage. And then you reach the decision to execution part of the flow. So here you have the D to E, the policy makes decisions and how to modify the existing services based on the data insight and also calls the service orchestrator, SO, to make the service modification. And now you have the last part, in fact, of closing the loop, where you have the execution back to the SDN controller, to the monitoring and controlling part, where you, in fact, the service orchestrator execute the service modification by instructing the SDN controller to apply new configuration to domain controllers. So this is an ongoing POC development inside ONAP that is, in fact, leveraging ZSM specification, and you can find more information on the ONAP wiki. Next slide, please. Another group which is aligned with the ZSM specification on closed loop is the 3GPP SF5. You have ongoing work into SF5, and especially we want to highlight two use cases. So the 6.1.6 is in a use case which is an action limiting for the assurance closed loop that is being specified into 3GPP SF5. And here the goal is to provide the consumer of an assurance closed loop as defined in SF5, the ability to limit the actions of this closed loop, the action that they can execute. So that when you enable this action limiting mechanism, the closed loop will only take actions that are within the scope of what has been defined by the consumer of this closed loop. So this is very related to what Ishan mentioned. You have specific mechanisms, specific services defined in ZSM 9.2 in the slide that Ishan showed you, very close to this behavior. And the other use case developed in SF5 is trigger-based assurance closed loop control state change. So in SF5, the primary closed loop that is being specified is linked to it's an assurance closed loop. Okay, it's a specific activity of a closed loop. And here the goal of the use case is to provide the consumer of this so-called assurance closed loop with the ability to set conditions that will in fact activate or change the state of the closed loop. And so you can, with using this mechanism of trigger-based, condition-based activation, you may be able to activate or deactivate in the 3GPP type of environment, the condition, the metric that you're monitoring, the conditions that will be triggered, it will activate or deactivate the closed loop based on this threshold crossing. Finally, if you go to the next slide, there is also another group that is leveraging the ZSM work on closed loop automation, which is in ITU. There is a focus group on autonomous networks, or FGAN, that is working on a proof of concept on intent-based closed loop. So really, in fact, it's leveraging two parts of the ZSM work, linked to what we have seen, for instance, from Magnus on ZSM 11 on the intent-based network management operation, and the work on closed loop automation. So here, the idea is to be able to generate made-to-order closed loops based on an intent specification, an intent expression, and to parse this closed loop to identify what are the components that are needed for the loop, especially right now from a syntactic point of view, but they're also working on a semantic model. And in fact, to automate the creation of the loop and also the adaptation, the be making able the recomposition of the loop during runtime. So you initially on the first point, you base on a recipe-based composition of closed loop and the ability to define new recipes. So the notion of recipe is in fact the so-called descriptor of what are the stages, what are the purpose you expect from the loop, and to be able to pick and choose the right component from that. Then the second point, selection of mechanism for monitoring, analyzing, and adapting the needs is in fact which component you need to choose to fulfill the different stages of the closed loop. And here they want to be able to introduce the fact that during the lifetime of a closed loop, you may need to update or change, adapt, in fact, which component will serve these different stages because you may have different needs or the network condition will have changed. And finally, in the continuous evolution is to be able to continuously adapt the outcome that is generated by the closed loop to really solve well. Here, the context was in fact for network slicing, so the evolving / customer requirements. And you can have more information on the focus group, autonomous networking focus group homepage. And there is also some code available to redo the demo. So yeah, the idea here was to highlight that there have been a lot of work done in closed loop automation in ZSM, and that we are starting to see into some related either open source group or standardization related group that this specification is being leveraged to enable proof of concept or new activities like in 3GPP SF. And then back to you again, Ishan, for the conclusions.
Yeah, so thanks, Laura. So what we saw, what is the takeaway from these slides? So essentially we specified enablers for closed loop code management, post and pre-execution coordination, and generic CL management interfaces, including the CL models. So that's a part of ZSM 9.1. Then we have solutions to automation scenario involving closed loops. So this is related to basic and advanced coordination, autonomous operations, closed loop, and can make to order closed loops. But this is a small subset of scenarios. The ZSM 9.2 has further scenarios, much more in detail. And finally, we looked at some analysis and requirements into the future work. What we expect is 9.2 to be published early next year. We are finalizing it currently. And similarly, 9.3 to also follow immediately after 9.2. And that's it from my side, Nurit. Back to you.
Thank you very much for the very comprehensive and insightful presentations about the work that we've done under the 009 series with the enablers, the solutions, and the advanced topics. And there is still way to go. And we're looking forward to see the continuation of that work. And by this, I want to move to another key automation technologies, and this is about enablers for artificial intelligence-based network and service automation. And I would like to invite here Abdul Raham from Nokia, which is the rapporteur of ZSM 012. So Abdul, please.
Thank you, Nurit. Let me quickly share my screen then. Right, so can you see the slides?
Yeah.
Yeah, great. So thank you for the introduction, Nurit, and thanks to all the previous speakers for the great presentations on the respective topics. So now we're going to talk about another element of the technologies that enable the automation in network and service management. And here we're going to be talking about enablers for artificial intelligence, empowered network and service automation. So specifically, what are the capabilities and aspects that we need to enable so that we can reach the AI assisted, the machine learning assisted full automation of the network. So the motivation for this work item, first, just to give you kind of an insight into it. The first aspect is that AI technologies are constantly becoming more integral part of network and service automation and network and service management. So the first question was how to operationalize these technologies into the automation and management framework. Now, how do we actually integrate it? And we're going to see later on that there are different ways and different levels of integrating AI technologies into network management. So we're going to talk about that in the next slide. Now, the second question was how to move from limited automation, portability and reusability to full automation, portability and reusability. So AI technologies integration right now is still limited to manual integration that requires, let's say, human intervention, and it's an intensive integration process that is dependent on the use case that is being addressed. So how can we actually enable the AI technologies to be integrated with less manual intensive work and to be more scalable across use case, domain, and scenarios? Now, the challenge for standardization is that how we can enable this multi-vendor, cross-use case, cross-domain, interoperable AI-based operations without limiting the capabilities that an operator has and kind of the governance that an operator has on implementing his solution. So this is the fine line where you need to kind of standardize certain capabilities that enable the AI-empowered automation of the network without compromising the flexibility that we try to give to individual implementations. So here we talk about, as I mentioned before, the different types of integration of AI technologies. Now, on the very beginning, we have this raw AI and automated operations. And the definition of raw that we have here is this limited view and use of AI potential. So we want to use AI, but we're not very clear about how this can be used. We use big data dumps to kind of analyze statistics, but we're not really, optimizing this whole data analysis process. We use AI in specific solutions, specific use cases, very limited. We use existing AI technologies to support our solutions, but we don't really, adapt it. We just kind of retrofit it a little bit just so it works in telecom or in other domain, network and service automation. Again, like I said before, it's manually intensive integration, so it cannot be done in automated fashion. There is no specific AI security measures that kind of cover the AI aspects of security. And there is a lack of standards that standardizes these capabilities that is related to AI. Now, as this use of AI evolved, we got to a point where we tried to optimize this whole use of AI a little bit. So now the AI techniques have been adapted to the network use. There are smarter data collection and processing techniques that is done based on the domain where this is being done. Now there are cross-use case solutions that can work on multiple use cases instead of having a specific solution for a specific use case. Large-scale application penetration of AI-based solutions. There is a know-how of how we can leverage AI and ML in network and service automation because of this, as this overlap between AI, ML, and network and service automation grows, then experts in this overlap gain more experience and know-how into kind of adapting either existing AI, ML solutions to network and service automation use cases, or actually inventing new solutions that are perfectly suited to network and service automation use cases. And of course, we see more AI-specific security techniques and methods to protect the network and service operations. And there are a little bit of emerging standards and basic interoperability. And now, as we are on the tip of this triangle, moving towards lean AI, with the goal to eventually reach intuitive AI autonomous ops, we are on this kind of intersection between the two middle, with a broad set of AI techniques being developed, with intelligent data collection and processing, ability to use AI as a service, with a full deployment and applicability of AI-enabled design, integration, and solutions, with a guaranteed AI functional safety, and comprehensive standards and increased operability. And this is right now what we are working on in this stage, with the direction to eventually reach this final stage in this AI journey, this intuitive AI and autonomous operations, with complete zero-touch AI operations, ability to perform machine reasoning, have a symbiotic human-AI interaction, complete mission autonomy, transparent, trusted, and open AI and machine learning use, and of course, reliable, robust, and distributed AI. So this gives us kind of the perspective, the big picture of where we started and where we want to go, and all the points in the middle. And just realizing that this is a multiple step journey that we're trying to approach strategically into defining these capabilities in order to move forward with the use of AI in network and service management. So here we have kind of what I like to call the AI verse. So we have, if we look deeper on this, I mean, if you look at this plot, it seems a little bit complicated, but let's look at each axis on its own. So on the x-axis here, we have the network domains. We have the device apps, so front end. We have the access, transport, core network, and back end. And here on the y-axis, we have the management, control, and data continuum. So you can see here in the different planes, we have the forwarding plane, we have the control plane, and we have the management plane. And on the z-axis, we have the domain to end-to-end management. So if you see for example, in the management plane, you move from the management domain to the end-to-end service management domain. Now, what we want to see is the integration of AI in all of these domains and across all of these axes. So it's not only about focusing on the management domain, but also extending the AI to the control plane, the forwarding plane, and also across other domains. So what we try to look at here is that we find the relevant scope for AI-empowered application placement. And we look at the business opportunities, the operator's preferences, whether the operator would prefer to have a distributed solution, a distributed AI presence, or a complex AI presence in the network. If you increase the distribution of the solution, then it becomes more complicated, but probably more efficient, and so on. You want to look at performance trade-offs based on the solutions that you're supporting, and of course the real-time requirements. Now, we also need to look at the management control data continuum as a whole, not only to look at the management plane and separate it from the control plane, for example, but to look at how AI can be integrated to work across domains together, and not in a kind of individual domain or individual plane manner. And finally, and most importantly, is to ensure that the artificial intelligence can function across domains, use cases, planes, and it becomes interoperable between use cases as a solution, and that it becomes kind of a unified and consistent way of empowering zero-touch automation through the use of AI. So now as we move toward what is the scope of this work item. So the scope of this work item is to define key enablers and functionalities that support the integration of AI in a seamless way in order to support network and service automation, to support deployment diversity, meaning that you give also kind of this flexibility aspect to the operator and you don't take away that from him, and to support trust and adoption of the AI, trust in the sense of, you know, protecting your network and service automation system by providing security measures and ensuring that the operator, the consumer, trusts the AI running in its network, and of course adoption that kind of provides this sort of ability to either fall back to legacy scenarios, or that AI assisted solutions, AI empowered solutions, or intuitive AI solutions can work together with previous solutions. So as we mentioned, that this work item would be providing a set of enabling areas and functionalities. So we need to kind of explain what are these enabling areas. So an enabling area, by definition, is a definition of a set of enablers that are these are capabilities or management services that are related to a given facet of automation, automation of management operations based on AI. So on the right-hand side, you have this figure showing different facets of automation. So you can have access to data, you can have triggering of actions, you can have inter-AI interactions, governance, or execution environment where the AI would execute their actions. Now, together, these enabling areas cover a comprehensive scope of AI-based network and service automation in ZSM. Of course, there is place for more enabling areas as our understanding and as our progress increases into this work item. Now, the expected outcomes are the following. So we aim at equipping the ZSM framework with some new capabilities that are completely designed and tailored for full AI operations enablement. Not only that, but also enhancing existing capabilities in ZSM in order to support AI ML specific management. Compact stage 2 specifications that are including a set of AI specific requirements. So these are AI specific requirements for use cases using AI or machine learning that capture the essence of what an AI needs in order to operate. Of course, this comes with the supporting management services that satisfy these requirements, of course, in complement to the existing ones in ZSM2. And a set of supporting deployment scenarios that involve multiple AI components and their interactions. And this serves as kind of a guideline to an implementer that tells them, okay, for a specific solution or a scenario, what we have envisioned is that it can be done this way, but of course the implementation specificities are left to the implementation, to the operator. So let's have a look a little bit at the individual enablers, kind of to explain each facet of these enabling areas. And we start with the execution enabling area. So the execution considers the infrastructure capabilities, and that these infrastructure capabilities should support AI application, execution requirements, and constraints. So we have different constraints in the networks in terms of real-time constraints or processing constraints, and this changes as this infrastructure is on cloud, on premise, on device, and where your solution is running. The execution environment may compose a computing continuum that we need to consider also. that this computing continuum is has diversity, whether it's sorry, there's some feedback. Oh, okay, that this diversity of execution environment needs to be considered. For different deployment options of the AI components, as we mentioned before, driven by real-time requirements need to be supported and planned for across multiple domains. The second enabling area is the data enabler. And from the name, we can see that these functionalities will be related to data, basically data access, data processing. So we need to ensure that there is access to the right data sets at the right time and in the right place. So we give strict license to access specific sets of data to the right places in order to perform training or inference or monitor performance. But we need to ensure that this is a secure data access. We need also to have a richer description and expressiveness of the data. That means that we need to consider either this data is labeled or not. We need to consider whether this data is suitable directly to go into training or inference. So this can be by pre-processing the data, preparing the data in a specific way to enter training or inference, handling corrupt data, providing trust in the data. Now, the data patterns are dynamic and they change over time, and therefore we need to be able to limit the validity of these models that use specific sets of data for training. As the data patterns or statistics change over time, we need also to kind of update these models in a specific way. Right. For the third enabling area on Enter AI, now we need to support the diverse learning approaches, whether it's supervised learning, whether it's unsupervised learning. Also, we need to support fully centralized AI versus fully distributed AI. So we need to look at all the possible AI implementations. We need to support multiple of these. For the action enabler, we need to support this integration of inference outputs into the network. So we need to be able to see what the AI application outputs and what it targets. Either it's a human operator or the machines or the underlying network resources. And we need also to ensure that the outputs toward humans can be interpretable to allow decision enhancements and making output actionable. And last but not least, the governance enabler. Basically, the governance talks about this high-level aspects of trust, of understanding of the AI, that the AI results have to be reliable, measurable, accountable. Outputs needs to be understandable to the human operator in different forms based on the use case. And they should provide information about the past, current, future activities of this AI solution. And they need to be integrated seamlessly, and their privacy and security needs to be ensured. So now looking at the current status and outlook of ZSM 12, so we have multiple areas in the work item. The first is the analysis of the existing scenarios. So we try to analyze these scenarios from an AI perspective, try to highlight any gaps that are related to these requirements and services. Analysis of ZSM2 list of services. We try to also kind of derive these new services or extend existing services based on the gaps that are identified in the analysis of the scenarios. Then the definition and requirements of each of the enabling areas, followed by M&S specifications for these individual enabling areas. We aim to develop new scenarios that are very specific to AI/ML and validate these scenarios after the M&S specifications are done. And of course, terminology alignment across ZSM to capture new terminologies that are related to AI. So finally, I would just like to add some words on, this journey towards full AI, full intuitive AI, autonomous ops, and the fact that we aim to provide cross-plane, cross-domain, and cross-use case use of AI to enable network and service automation, and that this will take time, but we are surely making great steps toward that. Now, we expect that there will be a stable draft by February to March of next year, and then soon after that, hopefully a publication of this standard. Now, thanks for your time and attention, and back to you, Nurit.
Thank you, Abdu, for the presentation, and definitely these enablers are key in order to enable this end-to-end automation. So we definitely expect to see this work progress and leverage also across the industry. Another important aspect to ensure that automation can be leveraged and adapted is actually to ensure that we have a secured environment and secure technologies. And I would like to invite Jingping to present the security analysis that she has done in ZSM 10 and as a rapporteur, and also the work that has been started on the normative part, on the security general aspects of ZSM framework and solutions. So Jing, please.
Hello, everyone. Can you see my screen?
We can hear you and we can.
Okay. So I'm Jingping from NOCA, the rapporteur of the ZSM 10 and 14. Today, I would like to share you the overall picture of the general security aspects on the ZSM framework. So what's the motivation to introduce the security work item in the ZSM framework? Because the ZSM framework has multiple management domains, and also it provided service-based management architecture, which could enable the multiple players from the different industry to integrate with ZSM framework for end-to-end service management. Also in ZSM, to enable the automation, many new technologies introduced. For example, AI and machine learning as just introduced by Abdul, and also the cloudified and the intent. All of those new technology also introduced the new threat services. That's why we need the specific analysis for the ZSM framework. In addition, ZSM framework is used to match the future network, including 5G network. And that's why impact of the potential compromising of the ZSM system could be very significant on the business of the operators and vertical service providers. In addition, in these years, many countries and regions define the mandatory laws and regulations, such as, for example, privacy, data security, and critical service protection laws. All of those laws need to be complied by the service providers. Otherwise, they could be suffer the big fine. So having native security can help to establish confidence and trust as the automated process deliver the intended business outcome. The study and work item aim to identify potential security threats and risks and specify new capabilities of the ZSM framework architecture to support automatic security controls for ZSM framework, also to align with zero-touch objective applicable end-to-end and per management domain. So as shown in this red picture, which also presented by Uwe before, ZSM Framework include end-to-end service management domain and also other network domains, as well as cross-domain integration fabric. The security threat and risk analysis on ZSM Framework will mainly target the end-to-end service management domain services and management functions. So the threat mainly include the deliberate threat, which performed by the malicious attacker, which intended to compromise the system. It could be also caused by the accidental threat, for example, misoperation by the benign user. The third, as mentioned, it could be regulation violation. So the methodology we used in this threat and risk analysis will be asset impact oriented. It could be qualitative or semi-quantitative, because fully quantitative could be has very high cost. And as mentioned, the threat categories include deliberate threat, accidental threat, and also regulation non-complex threat. The classified threats according to attack mechanism defined in the COM attack pattern enumeration and classification project of MIT. To mitigate the aforementioned security risks, 3 main security controls were proposed in the ZSM framework. And the first one is the dynamic access control, especially on the interface of the ZSM framework. It includes the external interfaces which face to the external customer, like the vertical customer. And also it could be the access control on the internal interfaces between the management functions of the different domains or the same domain. Especially for the external access control, the tenant should be well managed to control. They have the right permission to manage the resources assigned to them. The second aspect is the trust relationship, because the ZSM framework could be built on different domains, and it could be not all the management functions come from the different industry players. So the trust relationship between the different management domains is very important. That's why we need to build the corresponding trust relationship between the management domains, as well as management functions inside the same domain. The second aspect is the security assurance of the management functions deployed in the ZSM framework, to make sure there's no compromised management functions during deployment as well as during the runtime. And now we will explain the security controls one by one. And the first one is about the trust relationship. Because of the openness and the dynamicity of the ZSM framework, it introduced the new challenge to build the trust relationship, because the status, or especially security posture or status of the each management entity, could be changed dynamically because of the change of itself or its consumer or its producer. That's why the static trust relationship may not be suitable for the ZSM framework anymore. We need to introduce more advanced adaptive trust relationship mechanism. that require the new capability provided by the ZSM framework. For example, it should provide a knowledge-based trust evaluation service to evaluate or re-evaluate the trust words of a ZSM entity. So based on the evaluation result, the knowledge-based trust model adaptation service need to be defined to decide trust relationship and trust model between the two ZSM entities. According to the trust model and the relationship, the ZSM framework could apply the suitable security control on the ZSM entity as well as the interface between the entities. Also, during the runtime, those relationships can be rebuilt according to the change and other context of the ecosystem. Then the second security control is for the security assurance for the management function. As introduced by Ishan just before, there's an automation requirement on the CI and the CD process to faster deploy the management functions in the ZSM framework. Also, those management functions could be come from operator. It can also be introduced by other third-party player. So the security status of those functions could be quite diversity. And the vulnerability of the management functions could be explored by the adversary to compromise the management function itself, then attack other management function, finally endanger the whole ZSM framework and its consumers. And that's why we need the control to make sure the security, the management function deployed in the ZSM framework is always secured during deployment time as well as during runtime. Here we introduce some capability to enable the security assurance automation during the CICD process, which includes the security consideration. And for example, when deploy the management function, it should generate the security requirements according to the security profile of those functions, as well as the environmental context and threat intelligence. According to the security requirement, it could generate security test plan and security policies to enable this automated security test and security configuration on the management functions and on the whole system. After that, the system could have capability to monitor, detect, and report the anomaly during the runtime, and also trigger the remediation on the compromised management function. So because the ZSM framework provides the ecosystem to multi-tenancy to deploy and manage their resources and entrance services. So the resource between the different tenants should be isolated and protected according to the policy or SLA between the tenant and the ZSM framework provider. Circumventing isolation or other protection mechanism in the multi-tenancy environment could cause loss of the sensitive information and the service of the tenant, and also cause loss of the reputation of the framework provider. That's why the ZSM framework need to provide the capability first to provision tenant information and also expose corresponding management service to the tenant and then corresponding management resources to a tenant, as well as isolate and protect management resources for a tenant. And also, ZSM Framework is based on the service-based management architecture, which provides the open API to the internal and external consumers. Access control on the different consumers is critical to protect the resources not to be accessed by illegal or malicious users, because an adversary could exhaust management resources illegally or intercept and tamper the data policies for other legal users. Also, for the legal user, the consumer could misoperate on management services as high privilege administrators without right access control. That's why the ZSM framework needs to provide the capability to support identity management for management service, consumer and producer, and domain and cross-domain authentication and authorization, as well as provide security log connection and audit. And also, AI and machine learning is main enabler for the ZSM framework. And with the AI and machine learning, ZSM could provide the specific insight and also automatically make some decision. But recently, many AI machine learning systems were misled or evaded through data poisoning, model theft, or adversary examples. Therefore, AMR-enabled ZSM framework can be compromised because of the adversary attacks on the machine learning model and data. And so, to make sure the ZSM framework could be robust, the following security controls need to be applied on the data and machine learning model. For example, secure data and machine learning model supply chain, and secure machine learning model deployed in the framework during its life cycle, and also protect the interface to data and the AMR service. Also ensure trustworthiness of AI decision. So besides to protect the ZSM framework itself, on the other hand, ZSM framework could also be leveraged to provide the intelligent security services to protect the end-to-end service or network slice of 5G network. For example, in Inspire 5G Plus project, they used ZSM framework to provide the security services for the SLA, especially security SLA fulfillment and assurance during the life cycle of the 5G services and slices. So let's see the current status and next step for the security-related work item in ZSM. Currently, the study item ZSM 10 has already been published. And as next step, the normative work item ZSM 14 was created with following scope. First, we will define requirements on ZSM framework and reference architecture to support automatic and zero-touch security controls for ZSM framework to align with zero-touch objective. And also, we will specify a set of the security capabilities and to support automatic security assurance of the management functions include AMR-enabled functions, adaptive trust relationship, dynamic access control, as well as intelligent security services built on capability of the ZSM framework. And to complete and realize those work, we also leverage the workout from other SDOs, for example, from SA5, from ETSI, SAI, ETSI, NFA. We don't reinvent everything. We will leverage the specification from those groups to implement the same security specifications. Okay, that's all from my side. Thank you for your time. And you can get more information from the ZSM website. In addition, I would recommend you to read the blog related to the security aspects of the ZSM framework. Thank you.
Thank you very much, Ching. This is a very important aspect to accelerate adoption and trust in the automation process. So we definitely expect to see the normative work progress and again, leveraged by related organizations in the industry. I now have the great pleasure to invite Dr. Qin Lin, the Chief Scientist, Wireless Technologies in China Mobile Research Institute and the TSC Chair in Oran, to give us some keynotes about the outside view reflecting on ZSM impact, opportunities, and challenges. So Dr. Qin Lin, please join us.
Hi, Norit and everyone. Can you hear me okay?
Yeah.
Okay, great. Let me turn this on, and I need to share the screen first. Are you seeing my screen?
Yeah.
Okay, great. First, of course, it's a great pleasure to be joining everyone here because I think both on behalf of China Mobile and also on behalf of Oran Alliance, we have been in discussion of finding appropriate way for collaboration between the Oran effort and also ZSM program. And so let me use the next, I guess, about 20 minutes to share with you a little bit of our current progress and current status, and also kind of my initial thought about the synergy and the joint opportunities between ZSM and Oran. But it's just a very rough initial thought. So it's meant for follow-up further discussion. Okay, so first, I hope more or less the participants today have a little bit of awareness of our alliance, Oran Alliance towards Open and Smart RAN was launched in 2018, officially established in October 2018, that is, and currently we've enjoyed the participation of 317 companies. And with that, they bring forward over 5,000 technical experts globally, very actively participating in our technical activities. And as the co-chair of the Technical Steering Committee, let me share with you a little bit of our current structure. Under the Technical Steering Committee, we currently have 10 working groups and 4 focus groups, plus a open source community jointly launched with the Linux Foundation, as well as a minimum viable plan committee, MVPC, which I will elaborate a little bit later, that they're playing a great role helping our alliance to coordinate the works on the various working groups and focus groups. Okay, so our slogan is open, intelligent, virtualized, and fully interoperable RAN. I believe that with that, we do have a lot of joint interest and a common goal in next generation end-to-end networks, even though we primarily focus on the RAN part. And a little bit of summary of what our alliance have accomplished up to recently. We have jointly delivered 176 specifications, among which 70 are current versions. And we have released 4 open source software to the community. The 5th one is targeting next month and will be delivered. And starting in 2019, we have held an annual global plug fest. So the 3rd one this year is actually ongoing and will conclude around about the end of November this month. And in addition, due to many of the physical on-site events being canceled since early 2020, we have actually put together many of the original intent to be demoed and showcased in the various MWC onto a virtual form. So we have a virtual exhibition booth that is available on our website. Currently, since 2020, Barcelona MWC, we have now more than 100 virtual demos from our partners that is available. Very with the welcome of you to visit, and the link is on this page. And our release plan primarily is a way to coordinate our various working group and focus group work in a more kind of a time-aligned manner. So this year, the release 1 is focusing on the theme of open, which was delivered with all the technical specification that our alliance have completed as of March this year. As you can see, it covers the front haul transport, hardware reference design, software stack reference design, and also initially the open intelligent framework. And then the combination of our July batch of technical spec and our November batch of technical specs, we have a second release which focus more on not only placement of open theme, but also kind of introducing the first set of the intelligent offering, specifically traffic steering, which includes interference management, mobility management, and ICIC type of use cases, and the QoS/QoE optimization. These are all AI and machine learning enabled capability. And also RAN slicing is a big thing, but in this particular release, it's just the very beginning of the RAN slicing. RAN slicing will be a major part of our next release, which is scheduled in March next year. And also the initial phase of SMO, service management and orchestration. This I'm highlighting because I think from my very preliminary knowledge of the ZSM program, I think there are a lot of coordination and synergy that we could look into in those topics. And we have jointly launched a ORAN software community, which is our open source community with Linux Foundation starting April 2019. And as I said earlier, we have delivered 4 releases this beginning of July this year. We pretty much, since the establishment in April 2019, every 6 months, our software community would deliver a new release. And the next one is targeting next month, basically December, before the end of the year. And as you will see that a lot of the focus feature there, I think has synergy with the ZSM program as well. And all of this were jointly delivered by 12 projects. And you'll see that it's listed on this page, and the PTLs are listed there. They come from operator community, traditional vendor community, as well as new emerging player. So it's a very healthy, holistic mix of the leadership. Sorry. To support the continuous integration and continuous development effort of our open source community, we have established 3 open labs, one on each coast of the North America. So in Bedminster, New Jersey is our first community lab, open lab. And then subsequently in Silicon Valley, we have a second one, and also the third one is being established in Asia, specifically in Taiwan. Now, in addition to the open source communities, CICD needs from being provided by the 3 open labs, we have so far established 6 open test integration centers, OTICs, which is, as you can see on the map, is distributed across Europe and Asia, specifically 4 in Europe and 2 in Asia. And the 2 additional ones that are upcoming one, we will have a East Coast, North America, East Coast OTIC that is in the process being evaluated, and also not Asia specifically will be in Japan. And this OTIC is meant to provide stable, impartial, and open and friendly and consistent infrastructure for various software and hardware solution providers to come and try their technology and their offer based on ORAN specification, especially ORAN's test specifications for interoperability tests as well as conformance tests. And also many end-to-end use cases, prototype and testing would be done. It's about Global PlugFest. The current ongoing one will conclude by the end of this month. And it's being hosted actually at 7 venues by 17 hosts. And it's listed on this page, as you can take a look. Of course, those 17 hosts include many of the established OTICs. And all in all, there are 81 companies participating. And actually, these are unique counted companies, meaning that if a company is participating in the PlugFest in many of these 7 venues, we only count them once. So actually, if you directly add the participating companies from each of the 7 venues, or adding them together, we have a few hundreds of participating companies. Okay, so the scope in general includes the test based on ORAN Alliance's test specifications, examples such as the open front hole, which is the most mature one, and also the validating the early stage or demoing, for example, ORAN rig enabled use cases, okay, across multiple vendors. And then the feature packages like RAN slicing is also being prototyped and tried out in some of this venue, and as well as our hardware reference design and software reference design, of course. Now, there are a lot of news these days. I mean, this page I started producing maybe a year and a half ago, and it keep on increasing the content, updating its content. But now I don't even think this page is up to date enough. But I think we are interested in meeting from various major operators about their trials, their demos, or their interesting new capabilities demoed. Now, let's talk a little bit about specifically in the technical contents and our feature, the relationship and relevance, and which part of the ORAN scope would have affinity with ZSM, and from there we can maybe discuss how we can follow up to together to form a healthy and win-win collaboration. So first, I think I want to highlight the SMO function in our reference architecture. This is the service management and orchestration, which actually involve, I would say, 3 sub-modules. One is the traditional AM, okay, but of course we would like to make it more intelligent and with new capabilities. Secondly, sorry. The orchestrator, okay, the manual functionality. And the third one is the unique offer from ORAN Alliance. Basically, real-time control.
Okay, it seems that there is a technical problem here. Let's give Dr. Ching Li the opportunity to join us in a few minutes.
Nori, can you hear me?
Yeah, we can hear you now. There was a
Hello?
connected. Yeah, we can hear you.
Okay, sorry.
No problem. This is the technology. When we have zero touch, this will be automatically solved. But can you hear us? Hello, Dr. Chin Li. Yeah, so maybe until Dr. Chin Li is there, I will provide my presentation. Okay, I really hope that she will join us soon back. Okay. Okay, so I will show my screen 1 minute. Okay, so in fact, what I had to do is really to provide the conclusion and the outlook, but let's do the following, that I will share my slides now, and then when Dr. Chin Li is back, we will give her the floor. So Yeah. So I would like a little bit to conclude the presentations and to talk a little bit about ZSM in the industry landscape and the outlook. And again, when Dr. Jinling is back, we will come back to her back. So just a little bit to cap up again, what is our mission? So in ZSM, in ZSM, our mission is to define a future-proof end-to-end operable framework and solutions, end-to-end solutions, and key automation technologies to enable zero-touch automation emerging in the future networks and the services. The ultimate target is to enable autonomous operations with self-configuration, self-monitoring, self-healing, self-optimization, self-protection, which will be empowered with advanced cognitive capabilities and driven by high-level business policies. And in order to realize this vision, we had to define a new end-to-end architectural framework, which is designed for closed-loop automation and optimized for data-driven artificial intelligence algorithms. And this is actually what Uwe Rosenbach has presented as the architecture framework. And all these end-to-end solutions include the ones that Uwe presented on the cross-domain service orchestration and lifecycle management, and then the one from Zulan about end-to-end network slicing, and the one from Ishan about the CICD for automation. These are actually based on and leverage this architecture and ZSM services, and all the core or key automation technologies that we have defined or are defining on the intent, on the closed loop automation, on the AI enablers, the leveraging this framework and ZSM services, including the security part. If we look a little bit about the industry landscape for network and service automation, we can see that we have a lot of complementary efforts across the industry to enable this end-to-end automation. So if we look a little bit about the management domains where we're responsible for the orchestration of the resources, the SLA enforcement and assurance of the domain-wide services, taking the end-to-end parameters and translating that into the domain-specific resources and decide on the placement of the network functions. So we have domains that are responsible for just the key ones, responsible for the radio access domain management, and this is done by, by the SA5 and the O1 activities. And then we have the transport domain where ITF play a very significant role in the core domain management, which is done by the SA5. And then we have the end-to-end network and service automation, the solutions which are provided by ZSM and leveraging work done in SA5 and in ITF and O1 and TM Forum, and they actually satisfied the definitions in GSMA for the template and the slice types. And we have the end-to-end architecture, which is provided by the ZSM, also the key automation technologies and the security part. So this is a little bit to put the scene on the related activities in the industry. It's not a complete picture, but a high-level picture. And then if we try to reflect what we have done so far, so we have published a few documents which relate to the end-to-end architecture and solutions. So this is the requirements based on documented scenarios, the reference architecture, the end-to-end management and orchestration of network slicing, ZSM Landscape that allows us to understand what is happening in the industry and what can be leveraged to enable automation, terminology to ensure consistent use of the terms, and proof of concept framework to enable POCs to demonstrate the viability of the technology, and also to learn about the deployment, about implementation, and feed the information feedback back into the specification work. We have published also some key automation technologies. We published a report on means for automation. We looked at the major means to automate things and how we can leverage it in our work. We published the closed loop automation enablers and the study about or report about the general security aspects. We are still working on the end-to-end perspective. We are still working on the cross-domain end-to-end service lifecycle management. And on the key automation technologies, we are working on closed-loop automation solutions, advanced topics, intent-driven autonomous network, the study in AI enablers, the CICD automation, and security aspects. So this is a little bit to put the work that was presented today in the context of end-to-end architecture and solutions and the key automation technologies. And if we look a little bit about the value of our specification, it is unique. So we believe that for the end-to-end architecture and solution, we believe that work done in organizations such as C5, NFV, ITF, BBF, ONAP, OSM, Team Forum, etc., fit nicely into the ZSM architecture and can help with the solutions to enable the orchestration and automation of end-to-end services. And we believe that the ZSM specification also provides guidance to the implementation of the management services to achieve automation end-to-end. Regarding the key automation technologies, we believe that these technologies should be leveraged across the industry to ensure cross-use cases, cross-domain, cross-planning, interoperable, unified, and consistent automation and cognitive operations. And it's very important also to align with the security capabilities in order to ensure that the automated processes are secured and deliver the intended business outcomes. I think Uwe already quoted what actually Anil Rao said in one of the previous conferences, that collaboration is critical to accelerate the automation, and ZSM is the glue that holds them all together from the end-to-end perspective. So a little bit about what is happening in the industry. So if you look at the GSMA NG 127 on end-to-end network slicing, you can see that it is inspired by our ZSM architecture with the different management domains and the end-to-end and the service-based architecture. ONAP management components were mapped to the ZSM architecture. The 3GPP SA5 SBMA is aligned with the ZSM architecture, and SA5 management services are leveraged for the end-to-end solution. And ZSM core or key automation technologies are leveraged by SA5. And then the ORAN non-Ritamric architecture, or SMO and non-Ritamric architecture, was inspired by the ZSM architecture and principles. And Team Forum APIs are being studied to see if we can leverage and what we can leverage out of this. So this is a really good step that we've done. And to do that, we also established collaboration across the industry. So we established so far fruitful collaboration with key organizations such as ITU, Focus Group AN, SC5, NFV, ENI, ONAP, in order to promote the adoption and alignment and to ensure that automated end-to-end can be achieved. And we also work to establish the collaboration with other organizations. For example, as Dr. Ching Li already mentioned, that we are planning the next collaboration with the ORAN community. We're going for a third term, so the ISG has agreed to request the extension of the ISG for additional 2 years. The request will be submitted to the ETSI Director General and is expected to be approved. The intention in our group is to complete the work that we've started in the second term, and we want to work on the next level of details to enable interoperable solutions and ensure future operational processes and tasks to be executed automatically end-to-end. We want to explore and consider various deployment options and emerging business models. We want to identify new compelling use cases such as the network service, network of networks, digital twin, etc., and identify the missing parts that we can agree to work on. We want to assess and consider the implications of emerging technologies on automation. We want to maintain the overall mindshare and architectural integrity in ZSM and beyond ETSI, and to strengthen the collaboration with key organizations to ensure leverage of synergies and alignment. And we want to coordinate experimentation and showcasing of ZSM solutions, again, to demonstrate the viability of the technology and channel the results and lessons learned into the specification work. So areas that we consider to work on would be, of course, to continue the work on intent-based automation and cognitive operations, take it to the next level of specification, normative work, enablers for AI ML applications in support of automation, the governance services, unified and expressive data formats to support AI and ML, support for new IT, telco enterprise business models, support for the design time, support for network as a service, for network as of networks, to support of continuous integration, delivery, and testing, and to ensure that we have all the security capabilities to protect the framework, to protect the services, and to protect the automated processes. So just a little bit to provide my epilogue, end-to-end zero-touch networking service automation are essential to unleash the business potential of 5G and beyond. The ZSM framework is versatile and built on service-based principles, offering scalability, modularity, extensibility, and flexibility. It supports the transfer of autonomy from the operator to the network using intent-based interfaces. It integrates capabilities for closed-loop operation and coordination in support of the zero-touch operational goal, and it provides means to integrate AI-based functionalities, enabling operational autonomy. Alignment and leverage of synergies across the industry is essential to enable end-to-end automation and to ensure adoption at scale and accelerate time to market. It's important to highlight that end-to-end automation is a big deal, and it represents the industry next year's journey. And the ISG has agreed to and already planned for the third term work, and learnings from the real deployments need to be fed into the standardization work. The ISG is open for both ETSI members and non-ETSI members, and you are welcome to join us to help advancing the technology, help us to do it even better in the third term, and to demonstrate ZSM proof of concept. So this is from my side. I would like to thank you all and all the speakers from the ZSM group, and I would like to check if Dr. Chin-Ling is back and can now back to her slides. So are you back? Dr. Chin-Ling, are you now ready to continue the presentation?
Yes, I think so. Can you hear me?
Yeah, clearly.
Hello?
Yeah, we can hear you.
Okay, great. Let me continue sharing then. How many minutes? 5 minutes, 10 minutes? Do I have?
Yeah, you can even take 10 minutes, no problem.
Hello?
Yeah, can you hear me?
Okay, so let me just
go ahead. We don't
hear you, but can you see my screen?
We don't see. We see that you start sharing. Yeah, now we can see.
Are you seeing my screen?
Yeah, we can see your screen. Yeah. We can see your screen. Yeah.
Okay, just gonna work on this page. Okay, great. Well, I somehow
we can see this. Okay, you want to? Okay. Dr. Chin-Ling, we couldn't hear you before. Can you hear us? She's connected. I can see her.
Yeah, okay. You can hear me and you can see me, right?
We now can hear you, but we don't see the
Hello?
slide. Yeah, we can hear you, but we cannot see the slides.
Okay. Mine says that I am sharing, so I don't know why. So should I?
Maybe stop share and start sharing.
Okay, let me stop. Okay, I'll try to do it again then. Now can you see?
Let's wait. Not yet.
Hello?
Not yet. We're still waiting.
Okay. But you can hear me, right?
I can hear you. You need to start sharing again.
Stop sharing, okay. And then start sharing. Does it? So is the connection back?
Maybe in a minute. Maybe in a minute, because we see that you started sharing.
So
Maybe then you can just send us the slides, so maybe we can present, or just talk on them verbally.
Because I know that you just use this then.
hello?
Yeah, we can see the slides. Excellent.
Okay, I changed it to a different connection, so maybe it's
much better. Yeah.
okay, wonderful. So let me get started. Okay, so first, SMO and the non-real-time rig. This is kind of the block diagram in a way. You will see that the O1 related OAM functions and the O2 related will include IMS and also DMS. Okay, one is on the life cycle management of the for the deployment, and the other is more for the function, the infrastructure. And then the non-real-time rig, I think, is it's worth a special introduction, because the two rigs, non-real-time and the near real-time rigs, are kind of the new functions that we introduced in from ORAN. And then the non-real-time rig, as you can see here, is basically providing the core ML and AI enabled model training for the near real-time rig to use. And also it's a place where the intent-driven input gets translated, and also the enhanced information, etc., from internal would also come through this block. And then internally, there is an important API, R1 API, which is where the R apps, basically the non-real-time rig actual functions, these are all micro services that are integrated into this framework through this R1 combination. And then there is an A1 interface from the non-real-time rig to our near real-time rig. And so I think one of the things that was highlighted is that all the intent-driven automation goes through these key blocks. And then the near real-time rig that is connected with the non-real-time rig with inside the SMO, which is this block that you can see, and it has an important function, which is it hosting both the vendor provided or operator developed, as well as third-party delivered X apps, which are AI and machine learning enabled optimization control functions primarily. So I would say that if we would think about the management plan and the control plan differentiation, the SMO together with Mano is kind of appear with the management plan, whereas the near real-time rig is really more in the control plan. Okay, and then all the X apps enjoys our target is portability across different implementation of the near real-time rig. So we are working on the necessary APIs, as well as currently there's a discussion about starting the SDK related work as well. And from near real-time rig, the control going down and the data coming up primarily comes through the E2 interface. This is also a ORAN specified new interface, just like A1. Okay. And looking at the general reference architecture, this one I copied from the ZSM Framework documents. We can see that we really share a great philosophy. There's a great synergy in our philosophy. Like your major principles that I kind of copied down here: modularity, extensibility, scalability, and model-driven open interface, closed-loop management, support of the stateless management functions, resilience, and intent-based, of course. A lot of this has really a lot of similarity and affinity with our working group 2, working group 3, which is the non-real-time rig and near real-time rig working group, and also in many ways as well as the working group 6, which is our all cloud working group, where the manual functionality, the accelerator abstraction layer, as well as the lifecycle management of either virtualized or containerized network functions are being worked out by this working group. And finally, working group 10, which is our OAM working groups, that takes care of our OAM interface, which is O1 interface across all of the modules in the RAN. I think also shares a lot of common philosophy with you. So in a way, this affinity between ORAN Alliance and ESM are highly exemplified in working group 2, working group 3, working group 6, and working group 10 through its microservice-based architecture, the intent-driven automation, and zero-touch provisioning, as well as I think FCAPS. But here we are probably working on a subset of what sorry, ZSM covers, because ZSM has you are end-to-end coverage in terms of management automation. So you cover core network, transport network, as well as RAN, whereas we are only primarily focused on RAN. Now, if we look at the other direction, which is the relevance or importance of the ZSM solutions for our ORAN mission, we can see wide range of relevance. And just looking at the document you have already delivered in terms of network slice management, security, architecture, proof of concept framework, and open source, I believe that it can be matched to our effort in our working group 1, 2, 3, 6, 9, 10, and our open source community, our security focus group, and also our testing and integration focus group. So there is really a very exciting, I think, opportunity for us to have a solid discussion about the collaboration and the proper plan to deliver complement value and effort to our global ecosystem. Now, this is my last page, which is kind of an initial thought, but really, I think I want to not only just emphasize on our clear synergy and common interests, some of the representative keywords of intent-driven automation, data exposure, network intelligence, and also I think virtualization is also one of common interest. But also I think just the initial sorting through our limited understanding of ZSM's progress, we believe that we need to start with the architecture and terminology mapping, and your service management domain or your management domain versus our functions in terms of SMO, non-real-time rig, and maybe other functions, and also how would our functional nodes fit into ZSM's architecture, and also in terms of your management domain, we have both management plan and the control plan. How does this overlap or not overlap? Particularly, I think we have a question about our control plan, which is a very important part of Orion Alliance's technical scope. Is that outside the management domain work of ZSM? And then another small question is the integration fabric. We are very interested about that. Is that like a bus messaging infrastructure, or is it an analogy with our key interfaces, O1, O2, A1, E2? With all these questions, it may appear that we really have a very limited understanding of the ZSM right now, or really we need to maybe jointly share more information with each other with some follow-up meeting and discussion. And certainly, I think we should look to better alignment so that we can avoid unnecessary overlap or even potential conflicts or inconsistency, so that we can jointly really provide complementary values and efforts to a globally healthy ecosystem together. Okay, so that's my last page. Thank you very much, and look forward to discussion.
We really appreciate it's a pity that we don't have any longer time for discussion or questions, but thank you very, very much for your presentation. It was very good to see the common ideas and the common synergy, and it just encourages that we need to work close together. I think alignment and leverage of synergies is key here. So let's have our meeting together and see how we can collaborate and benefit and support each other.
Okay, definitely look forward to it.
Excellent.
Really, yeah.
Excellent. So I think I would like to thank all the speakers and all the presenters for the very good workshop, and for Layer 1 to 3 for giving us the flow to do that. And since we don't have a lot of time for questions now, so please contact us, send us questions, comments, proposal, and also join us in helping and help us to do it better. Klaus, I think you want to provide a closing remark.
Yes, thank you, Nora, and thank you for this great presentation, Dr. Schilly. So we're happy to have you here on board, and got your thoughts about the collaboration between Orion and ZSM. And that was really great to see that. Yeah, and Nora, I like to second what you said. A deep thank you to all the speakers, all your participants. I think it was a great event of today, and let us work with the topic. It's an interesting topic to work on. Yeah, thank you for your time. Really give back to you.
Okay, so I think we close here the session. Thank you very, very much, and bye.